Dear colleagues, welcome to this special session. Marina Revalski will talk, and I will say a few words. I saw first time her name in 2010, 12 years ago, from paper in the archive, Bondarenko, Radchenko, Vezovka, optimal symptotic bound for spherical design, looking after some citation of my shy paper from 90s. And 3 years later, the paper appears in Annals of Mathematics. You see, it is one sentence abstract. The paper is short for Annals, short for, so only 10 pages, with short abstract, so it's enough to prove that the result was quite significant. One more proof that it's significant. The first named after Andrei Bondarenko won the Bulgarian related prize named after Vasil Popov. It's one of his papers was this. Okay, the disadvantage of these designs which she constructed together with Bondarenko and Radchenko was that they were not explicit, and it was slightly improved in the next paper, well separated spherical designs and constructive approximations. Okay, and then the next great result came with the proof that sphere packing in 8 dimensions, the usual suspect, the Korkin-Zolotaryov lattice, gives the highest packing density. You see again one sentence abstract, short title in Annals, this time longer, but quite significant paper, quite significant result. And then the attention, the appetite was enormously rising. And together with Henry Konop, Kenav Kumar, Steven Miller, and Danilo Radchenko, she turned to sphere packing problem in dimension 24, when again the usual suspects, the Illich lattice was proved to be optimal, to give the optimal sphere packing density. And in both cases, it was building on her advance on finding some magic function for the dark variation of linear programming. Already in the Congress in Brazil 4 years ago, Marina was a good candidate for the Fields Medal, but it seems that she was one paper in Annals short of this. So next paper is to appear in Annals with the same co-authors as for the sphere packing in 24 dimensions. And now they proved the optimal, the universal optimality of the same two lattices, the Korkin-Zolotaryov and Illich lattice. Okay, so I will not continue with this and give floor to Marina.
I would like to thank for the introduction and for the invitation, and I apologize that I can be present only virtually, but maybe we should remember that coronavirus is still with us. It did not disappear yet, unfortunately, but I hope that soon I will be able to visit Sofia in person. And so today I will speak about Fourier interpolation pairs and their applications. And so here's the kind of problem I'm considering. So let me recall a definition of the Fourier transform. So suppose that f is a function in Euclidean, defined in Euclidean space, and we assume that this function is reasonably nice. Then for this function, we can define its Fourier transform in the following way. So it's integration of our a function against a flat wave, where flat wave depends on a new parameter y. So this creates a kernel for us, and integration of our function against this kernel gives us its Fourier transform. And this, well, this transform is very fundamental in analysis. So it's essentially the harmonic analysis of a function in Euclidean space. And also, as we know from various uncertainty principles, that it's very difficult to control both function f and its Fourier transform simultaneously. And so there are many ways to formulate and capture this uncertainty in mathematical theorems. And so one of the definitions motivated by this phenomena is the definition of Fourier uniqueness pairs. And so we would say that the pair of functions lambda lambda tilde is a Fourier uniqueness pair if for any function f in a certain function space V, vanishing of a function on the set lambda and vanishing of its Fourier transform on the set lambda tilde imply vanishing of function f itself. And so another way is first I would like to draw your attention to the fact that, of course, this definition it depends on our choice of the space V. And so as the space V, we can work with different spaces. And usually it's nice to work with big spaces, like spaces that are dense in a bigger for function spaces in some sense. For example, in my talk, I will mostly work with the space of Schwarz functions. However, not always. And so here's one classical example of the Fourier uniqueness pair. So let's fix our dimension of our Euclidean space to be 1. And let's consider the set lambda to be the set of integers and the set lambda tilde to be the complement of the interval minus 1/2, 1/2. And then it's a classical result from function analysis that if we have a function in a reasonably nice function such that its Fourier transform is well defined, and at the same time the function vanishes at all integers and its Fourier transform vanishes outside of the interval minus 1/2, 1/2, or in other words, its Fourier transform is supported inside of the interval minus 1/2, 1/2. Then for function f also vanishes. And so one way to formulate this result, we can actually be more precise and formulate what is known as the Whittaker-Shannon interpolation formula. And this formula not only tells us that the pair of sets Z and complement to the interval minus 1/2, 1/2 is a uniqueness pair, but it also tells us how to reconstruct a function with so that if its Fourier transform is supported on interval minus 1/2, 1/2, and we know values of functions at integers, then we also know how to reconstruct this function. And so this is this famous formula. So we know that this we can here we can use cardinal sign functions as our interpolating basis. So the cardinal sign functions, they are exactly functions with the property that their Fourier transforms are supported on the interval minus 1/2, 1/2. And also the cardinal sign functions, they vanish on all integer points except for 0. And so if we consider shifts of cardinal sign functions, then we will get interpolating basis, and we will be able to reconstruct function from its values at the integers. And so this classical example motivates our next definition. So now let V and W be two spaces of functions in Euclidean space, and we say that lambda lambda tilde is a Fourier interpolation pair if there exist collections of functions A, L, A, here there is a typo, this should be A tilde M, probably in some other space W, such that each function F in our space V can be reconstructed from its values on a set lambda and its values on a set lambda tilde. And so here I write sum over two of the sets, which implies that both sets are countable, but this is not always the case. For example, this contradicts our previous example when one of our sets in a Fourier uniqueness pair was countable set, and another was complement of the interval, so an uncountable set. And so in this definition, of course, we think we should interpret these sum signs in a somehow free way. So sometimes they should be replaced, obviously replaced by integrals with respect to certain suitable measure, but I will leave out these technical details. And because the Fourier uniqueness and Fourier interpolation pairs I'm going to speak later, I will consider the case when both of these sets are countable and even closed discrete subsets of Euclidean space, or almost like that. So. And so now we can make our definition, if we can demand even stronger property. And so the property is the following. So now we have considered pairs lambda and lambda tilde such that information about restriction of f to lambda and its Fourier transform to lambda tilde gives us complete information about f. So we have a way to reconstruct our function uniquely from these restrictions. But now the question we can ask ourselves, is this information redundant? Can we make our sets lambda and lambda tilde even smaller? And so if we cannot make, if the information is not redundant, if information is just enough to reconstruct all functions f in the space V, then we would say that this pair is a free Fourier interpolation pair. And so we can formulate it in the following way. So let's consider certain spaces of functions V of lambda and V of lambda tilde be certain spaces of functions now on our sets lambda and lambda tilde respectively. And so we assume that a restriction of function f, which is in a space curly V, will also belong to this. So its restriction to the set lambda will always belong to the set V of lambda, and its restriction to the set lambda tilde belongs to the set V of lambda tilde, so the restriction of its Fourier transform. And so what we would like the property we would like to have is that this restriction map, it is actually an isomorphism between the space V and the product of spaces V of lambda and V of lambda tilde. And also we expect that this map should be an isomorphism. So this map should be an isomorphism, so it should be an inverse to this restriction map. But so now we have given so many definitions. Do we have any examples that do satisfy these definitions? And so we already know about the classical Shannon-Whittaker formula. And actually, this formula has many generalizations. For example, the nodes in the interpolation formula, they don't have to be regular. So there are irregular versions of the Shannon interpolation formula. And there are many more examples of Fourier uniqueness pairs. But till now, for some reason, literature mostly covered the cases when at least one of the sets lambda or lambda tilde is not countable, or at least the cases when both of these sets are not discrete. And so one of the results we discovered in the course of our solution to geometric optimization problems was a discovery of Fourier interpolation formulas, Fourier interpolating pairs lambda and lambda tilde such that both sets lambda and lambda tilde are discrete. So maybe here I would like to thank Andriy Bondarenko for the conversations we had with him in 2015 before we even believed that such formulas could exist. And so together with Danilo Radchenko, in 2017, we have proved the first, maybe easiest version of a formula like this. So we have shown that on the real line, so in Euclidean dimension 1, these two sets, lambda and lambda tilde, which consist of square roots of all plus and minus square roots of all positive integers, so that these two sets, they are essentially the Fourier uniqueness pair. And so the exact statement I will give you in the following slides. And so we have shown that this is essentially the Fourier uniqueness pair and also Fourier interpolation pair. And after some for finite corrections to this formula, it's also the free unique interpolation pair. So it's the best possible uniqueness pair we have considered so far. And so that then also in our, I would say maybe say in our joint work with Danilo Radchenko, but also Henry Kohn, Stephen Miller, and Abhinav Kumar, we have shown another version of this formula, a more complicated one. So this is a simple Fourier interpolation formula, but we have proven a Fourier interpolation formula of second order. But I will come back to this formula later, and I will also talk about, when I will speak about applications of Fourier interpolation pairs. So another, I think, very beautiful and rather mysterious result was obtained by Andriy Bondarenko, Danilo Radchenko, and Christian Seip. They've shown that there is a Fourier interpolation formula associated to zeros of any L function. At least a L function for GL2. And in particular, there is an interpolation formula associated to the zeros of zeta function. And so here, we cannot, for this formula, we cannot work with space of Schwarz functions. Here, the space of functions for which this formula is well defined has to be worked out carefully. Also, maybe so I want to say that this formula, one can see it as this generalization of the while summation formula associated to the zeros of zeta function. Only now it's for this formula is actually this is deformed by adding one more continuous parameter to it. And so maybe final thing I would like to say that actually the interpolation of this Fourier uniqueness pair, it's indeed a Fourier uniqueness pair according to our definition, only if the Riemann hypothesis is true. And in that case, we will know that indeed lambda tilde is a subset of the real line. But if we don't know the Riemann hypothesis, formula still makes true, because we can consider a space of functions which can be extended from real line to the complex plane. And then the evaluation of a function at the roots of non-trivial roots of zeta function still makes sense. And so these two examples, they have one thing in common. They have very rigid algebraic structure. And however, it seems that this property of being the Fourier uniqueness pair is not an algebraic property. It seems that this should be analytic property of the set. And eventually what should matter is really the density of points in the set normalized in a correct way, and not their precise algebraic structure. And so maybe first move in this direction is the result of Ramos and Sousa, who showed that we can take the first formula on my list, the formula we have proven together with Danilo Radchenko, and perturb it a little bit. And so what they were able to do, they were able to add small perturbations to each node, and this perturbation should become smaller and smaller as our nodes move farther and farther away from zero. So in this example, the algebraic structure still plays important role. However, we see that it doesn't have to be that strict. And so this result was followed by a result by Mikhail Sodin, Alexei Kulikov, and Fedor Nazarov. who proved that Fourier, who wrote at least a preprint on, I don't know, maybe it already appeared in also as a journal paper, but in 2020 they announced the following beautiful results. So they analyzed Fourier uniqueness and non-uniqueness discrete pairs, and they showed that indeed they could define the notion of supercritical and subcritical density, and pairs of sets with supercritical density, they are Fourier uniqueness pairs, and pairs of sets with subcritical density, they are non-uniqueness pairs. And at the same time, it seems at the moment that this question of being Fourier interpolation pair or being free Fourier interpolation pair, it still cannot be approached directly by analytic methods. And so here, some kind of algebraic structure is still needed to obtain those kind of results. And maybe also there is a recent, very recent result by Ramos and Stoller, and they were able to construct discrete Fourier interpolation, so closed discrete Fourier interpolation spheres, also pairs, also in higher dimensional Euclidean space. So all these examples which I showed you before, they were all construction of Fourier uniqueness or Fourier interpolation pairs on the real line. And we also had generalization of these formulas to higher dimensions, but they worked only for radial functions, and therefore they were essentially one-dimensional. And what Ramos and Stoller have done, they've shown that Fourier uniqueness pairs, the discrete Fourier uniqueness pairs also exist in higher dimensional Euclidean spaces, even though the description of this pairs is not explicit. And in higher dimensional Euclidean space, we're still quite far away from constructing free Fourier interpolation pairs. So all the pairs we can construct now, they are redundant. They probably contain more information than we actually need. And so here's a theorem of Sodin and Kulikov. So this is exactly the condition they have found for the density of nodes. And so they've seen, they suppose that our pairs lambda and lambda tilde, they're given by the sets, by the sequence of, by points lambda g and lambda g tilde. And it's also logical to think of this nodes as being ordered on real line, maybe symmetric around 0. And so what they show that the densities, so here we're fixing two numbers, p and q, two real numbers, such that their inverse powers equal to 1. And so they defined this condition to be as a condition for supercritical density, and this condition for the subcritical density. And then you see that in our the first formula from the previous slide, the density is exactly critical. So in our first case, we have to choose p and q to be equal to 2, and then we will get this case of square root of positive integers. So this will be exactly critical case. And so the theorem by Sodin, Kulikov, and Nazarov tells us essentially, so I'm writing it in a very vague form, it's that supercritical density applies uniqueness and interpolation, and subcritical density implies non-uniqueness. And so, but now let me come back to the first formula of interpolation formula on my list and tell you a bit more details about how is it precisely formulated, and also a few words about our methods of the proof. So this is the theorem we've proven together with Danilo Radchenko in 2017. And we have shown that there exists a collection of Schwarz functions with the property that any Schwarz function P on the real line and any point X on the real line, we can reconstruct the value of P at the point X by the values of p at square at plus minus square roots of integers, values of the Fourier transform of p at plus minus square roots of integers, and also as a finite dimensional piece of extra information, namely two-dimensional, we also should know the derivative of p at 0 and the derivative of its Fourier transform at 0. And so this tells us that actually the set I showed you, it does not exactly satisfy my definition of Fourier uniqueness pair, because we still have this extra piece of information we need for complete reconstruction of the function. But up to this finite dimensional defect, this is indeed the Fourier uniqueness pair. And so here, this is how the interpolating, so these functions an and a in the Fourier transform of an. This is my interpolating basis. And this is how the interpolating basis looks like on a plot. So if you ever worked with, for example, orthogonal polynomials, I think they behave pretty much like orthogonal polynomials, or like polynomial interpolating basis for finite number of nodes. So here there is no, you don't have that many surprises. So on this plot, what I do, I don't consider my initial basis an, but instead I consider its symmetrized version, symmetrized with respect to the symmetries the real line has about 0. And this is just a technical aspect. And so, as I already told you, that this Fourier uniqueness pair, it's also a free Fourier interpolation pair. And so, if we consider a map from which restriction map from the space of Schwarz functions to the space of functions on my square roots of integers, so this would be essentially a map from functions to sequences. And of course, if our function was a Schwarz function, then we know that it decays faster than any inverse power of a polynomial. And of course, the sequence we obtain by considering its restriction, it will be a rapidly decaying sequence. And so let this small Gothic S, it will denote for us the space of rapidly decaying sequences. And curly S will denote the space of Schwarz functions on the real line. And then we have this map, psi, which maps function on Schwarz function to its to the following sequence, which consists of the derivative of function at 0, derivative of its Fourier transform at 0, values of function at square roots of integers, and values of its Fourier transform at square roots of integers. And so now the question is whether we can invert this map. And it turns out that this map cannot be inverted because it is not a surjective map. So the image of this map, it will be only a subspace of this direct sum. And this happens because all Schwarz functions, their values at these points, they satisfy certain relations. And these relations, they come from the Poisson summation formula. So what happens is that if we have a Schwarz function, then we know that our Schwarz function will have to satisfy the usual Poisson summation formula with respect to the lattice of integers. And so if we take, of course, integers, and in our formula, it means that if we look at only the values of our function, not at square roots of integers, but at square roots of perfect squares, then we will have this relation between the values. But these are not this is not the complete list of relations between these values of a function. We also have one more Poisson summation formula, and somehow this formula, it comes to us from dimension 3, and it's related to the Poisson summation formula in three-dimensional Euclidean space associated to the cubical lattice. So here R3 of n denotes the number of points in three-dimensional cubical lattice of length square root of n. And so we also have this kind of relation, but this relation is a bit more complicated than the usual Poisson summation formula, and it also will involve the derivatives of our function at 0. However, these are the only two, so we have shown with Danilo, is that these are the only two linear relations. And so now if we think of our map F map site will map Schwarz functions into the kernel of this linear functional L, which is given in the formula below. And then map phi, it's actually an isomorphism between the space of Schwarz functions and the kernel of this linear map L. And so now let me tell you a few words about the proof of the Fourier interpolation basis. So first, for technical reasons, it will be more convenient for us to work separately with odd and even components of Schwarz function. Of course, every function on the real line, it can be uniquely split into a sum of an odd and even function. And what we can do, we can write our interpolating formula separately for odd and even functions. And so this is what we are going to do for a technical reason. And so we have this rather mysterious interpolating basis, which we have somehow conjectured so far, but did not find what this interpolating basis should be. And so here we will use as I think rather standard method from number theory, which is if we have an interesting sequence, let's consider a generating function for this sequence. And then if our elements of the sequence have some remarkable properties, then the generating function itself also should have some remarkable properties. And so we are forming the generating series for the interpolating basis Bn. And so here we choose, here x is our variable at the real line, and tau is a variable at the upper half plane of complex numbers, so the set of all complex numbers with positive imaginary part. And so then e to the power pi tau becomes our formal variable for forming this series. And so we also consider the function f tilde, which would be generating series for the Fourier transforms of the functions Bn. And so now what can we say about just this generating series? So now we make the following observation, is that we can, if we imagine that our interpolation formula, it is indeed, it exists and it has all the properties I mentioned to you, and it means that it should work for all Schwarz functions. In particular, it should work for complex Gaussians. So now here again, tau is a variable at the upper half plane of complex numbers, and we think of this function as a function of x, where x is a variable on the real line. And so this function, it will be a complex valued Schwarz function, and therefore interpolation formula should be true for this function as well. And so now this is the moment where we use this special algebraic structure of our nodes, because if we substitute square root of n into the complex Gaussian, we get exactly this exponentials as a function of tau. And so the interpolation formula applied to complex Gaussian is equivalent to this functional equation for the generating series f and f tilde. So now we remember that somehow if you look back at our definition of the generating function, we see that except for this functional equation I just showed you, they also secretly satisfy two more functional equations, namely these both functions, capital F and capital F tilde. They are periodic in variable tau with period 2. And this again, this is true because of the algebraic structure of our Fourier uniqueness set. And so we have these two functional equations together with this more complicated functional equation. And so now what happens is another algebraic coincidence. Now, if you look at all the transformations of variable tau that are involved in this formula. So we will see that we have this transformation, which is shift by 2, tau goes to tau plus 2, and we have this inversion in the upper half plane where tau goes to the -1 over tau. And what happens is that these two transformations of the upper half plane, they form a discrete subgroup in the group of all transformations of the upper half plane. And so this will play important role in our proof, because the existence of this discrete subgroup means that now we can apply all the power of the theory of modular forms and actually solve this functional equation explicitly. And so this is what we are going to do. So here, fortunately for us, people have already thought a lot about functional equations of this type and developed actually several methods how to address such questions. And one of the well-established methods is the method of contour interpolation by meromorphic kernels. And so we can search for our find our function f in the following form. So here k of tau z is a certain explicit meromorphic kernel, which is given in terms of modular forms and modular functions at the upper half plane. And these functions, they are meromorphic with respect to the congruent subgroup gamma 2, which is a discrete subgroup in the group of all holomorphic transformations of the upper half plane. And I will introduce this group in my next slide. And here integration is taking over path gamma tau. This path, it connects points minus with this path that's contained inside of the upper half plane. And it connects points -1 and 1, which are exactly on the boundary of the upper half plane. And also, what is maybe not such a good news, but this path, it will depend on tau, so that our function is indeed a holomorphic function of variable tau. And so this is how this looks like. So this is the definition of the group gamma 2. So group gamma 2, it's a group of all matrices. As a group, it's a group of all matrices size 2 by 2 with integer entries and determinant 1. And moreover, this matrix satisfy one more condition. Okay, here there is, I'm sorry, there is a typo. So this matrix A, B, C, D, it's not congruent, of course, to 0. Otherwise, it would not be very meaningful. It's congruent to the identity matrix modulo 2. And so we see, and then this group gamma 2, it acts by linear fractional transformations or Möbius transformations at the upper half plane. And this is a nice discrete action. It has well-defined fundamental domain. And we can consider holomorphic functions which are symmetric with respect to this action. And in particular, we have non-empty spaces of modular forms. These are functions which are almost like not exactly invariant under this action, but almost invariant with a well-behaved correction term. And so, but this is how our integration contour looks like. So I've told you that the kernel k of tau z, it's a kernel, it's a meromorphic kernel. And if you look at it as a meromorphic function in integration variable z, then this meromorphic function will have single poles exactly at those points which are equivalent to the first variable tau under the action of gamma 2. And this is more or less how, so here I draw this point tau, and I think it's, of course, this is some anonymous point at the upper half plane, but in fact, I've chosen point I as my prototypical point at the upper half plane. And here I mapped for you several of its in these blue points. These are several gamma 2 translates of the point tau. Of course, there are infinitely many of them, but all they all accumulate closer to the boundary of our upper half plane, closer to the real line. But here are the points which are higher up in the complex in the complex half plane. And so now I have to choose my contour tau and changes as I change point tau itself, so that my the integral would be a holomorphic function. But fortunately, this, like with a little bit of work, we can see that this indeed can be done. And our function, generating function f, it's well defined, and it also has good properties in terms of its growth in both variables tau and z. And this allows us to prove the Fourier interpolation formula. And now also with this integral representation for as generating function, we also have integral representation for the interpolating basis. So this is an interesting information for us. And here also Bn, here again, we are taking these integrals over a contour going from -1 to 1. But in this case, the functions Gn, they are weakly holomorphic modular forms of level 2 and weight 3/2. So the good news is that these functions Ga, Gn, they are actually holomorphic functions at the upper half plane, but they have what we call their poles only at the boundary of the cusps, at the boundary of the upper half plane. And therefore here, for this contour integral, it does not matter which contour inside of the upper half plane we choose. And so in this sense, we do have explicit formula for our interpolating basis Bn. And so here there is one more nice surprise, is that in general, this is probably this is the our interpolating functions as explicit as we could get them. This is maybe most explicit form we could have computed for them, for all functions except for one. So what turns out that in our interpolating basis, this of the function C0, which a bit stands out. So this was the interpolating function which was associated to the derivative of our Schwarz functions at the 0. So it turns out that this function, it still has this kind of integral representation, which is a bit does not coincide with the formula I gave you before, but that's because before I worked with even functions, but this difference, it will be actually an odd function at the real line. So here formula is a bit different, and I did not show you that formula, but it's still very similar to the formula on the previous slide. But here we can further simplify this integral, and this formula of the interpolating basis is indeed an elementary function. It's a ratio of sine and sine hyperbolic. And maybe the last thing I would like to say about this formula, that this Fourier, so this function, it's a Fourier eigenfunction, and it was proven by Ramanujan in 1917 that indeed this function is a Fourier eigenfunction. So maybe in one of the lost Ramanujan's notebooks, also the rest of interpolating basis is given somewhere. So, but we don't know that yet. And so now let me speak a little bit about interpolation. So as I told you, my motivation for studying this type of Fourier interpolation formulas came from applications to geometric optimization problems, namely to packing problems and to energy minimization problems. But for these goals, the simple formula we have proven together with Danilo is not very helpful. And so we have proven that formula maybe as a baby case, to try our muscles before we attempt to prove this more complicated second order interpolating formula. And so together with Henry Cohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko, we have proven this second order interpolating formula. And because our motivation for proving this formula came from geometry, we have proven this formula for dimensions 8 and 24. But of course, the formula would be true also in other dimensions. But we were a bit lazy to prove its most general case. We have done it for these two dimensions. And so now let D and N0 be either 8 and 1 or 24 and 2. So here 8 and 24, they stand for the dimensions, dimension 8 or dimension 24. And 1 and 2, they actually correspond to the squared length of the shortest vector in E8 lattice and Leach lattice, and they will go. So N0, it's a number where our interpolating formula will start. So in higher dimensions, to reconstruct Schwarz function, because we would have more and more relation, more and more different types of Poisson summation formulas or Voronoi summation formulas. So it means that we actually need less information, so we can throw away finitely many square roots of, in this case, of even integers, and we don't have to always start from 0 or start from 1. In higher dimensions, we can start a bit later. And what we have shown is that there exists a collection of radial Schwarz functions, and here we have Schwarz functions a and bn, a n tilde, bn tilde, and here I apologize, but these bn's, an's, they're not the same as an's and bn's in my previous slides. So here it's new interpolation formula and new definition of an's and bn's, and I was a bit too lazy to give new names to the variables. So what we have, so now we can reconstruct a Schwarz function, a radial, this time it's a radial Schwarz function, and we can reconstruct it from its values and values of also values of its derivative, and same information for its Fourier transform. So this time we are taking not square roots of integers, but square roots of even integers. So it's twice less information in some sense. However, at each point we are evaluating we are computing not only the value of the function, but only the value of its derivative. And so this somehow compensates for taking sparser set of nodes. So maybe one more thing I want to say that, of course, I think of my radial function now as not as a function of a point in Euclidean space, but rather as a function of distance from this point to the origin. And so and here I abuse notation a little bit. So here when I speak of the Fourier transform, I actually mean the Fourier transform in d-dimensional Euclidean space. And for radial functions, this becomes equivalent to the Henkel transform. But when I speak for derivatives, I think of derivatives in this radial dimension. I think of my function f as a function of distance to the 0 one-dimensional function, and the derivative is this derivative with respect to the distance from point to the origin. And so we had a formula like this. And now I would like to show you how this formula can be used to solve geometric optimization problems. And yeah, so again, sorry, before I do that, I would also to tell you a few words about how to find these functions an and an tilde. So here we can also consider generating functions. And now because we have two types, or really four different types of functions in our interpolating basis, we can consider this more complicated generating functions. And the generating function, it's not periodic in variable tau anymore. Now it is linear periodic. So we are again forming the generating function f. and its counterpart generating function f tilde. And now as we apply interpolation formula on the previous slide to the complex Gaussian, we again get this type of functional equation, which is already familiar for you. So now we remember that f and f tilde, they are actually linearly periodic, and so they satisfy this type of functional equation. And fortunately, again, the methods in the theory of automorphic forms, we still can, maybe with working a bit harder, and sometimes much harder, we still can solve this functional equation explicitly and find integral representation for the function f and for the functions in the interpolating basis. And also we can have quite good control over the growth of this function f in both variables x and tau, and it helps us prove analytic aspects of our interpolation formula, such as convergence, and for example. And so now here are the applications we have for this kind of interpolation formulas. So one application is sphere packing problems in dimensions 8 and 24. Another is the universal optimality of E8 lattice and Leach lattice. So recently, similar types of interpolation formula that were applied by physicists to certain optimization problems in conformal field theory, and there are papers about optimization of, so for example, like very nice paper by Henry Kohn and Felipa Concalves, where they applied this type of technique to optimization problems and functional analysis to various uncertainty principles. And so this is also an ongoing project with Danilo Radchenko, Hakan Hedemalm, and Andrei Bakan, is to use this type of formulas to prove interpolating formulas for differential equations, in particular for Klein-Gordon equation. And so as I still have 5 minutes, so let me speak about the first of these 4 applications, namely the application to the sphere packing problem. And so this actually, my research in this area, it was motivated by this result by Henry Kohn and Noam Elkis, and they adopted the linear programming method to sphere packing problem in Euclidean space, and they proved the following theorem. So let R0 be some fixed real positive number, and suppose that we are able to construct an auxiliary function f, which is a Schwarz function, and here Schwarz function, it's not the condition from the original paper of Kohn-Elkis, but it will be good enough for our purposes. And so suppose that we have a Schwarz function f, which satisfies these 3 conditions. So first function is non-negative outside of the ball of radius R0. Next is that its Fourier transform is non-negative, and our function is normalized so that the value of function at 0 equal to the value of its Fourier transform at 0 equals 1. And now you see that after we fixed this normalization, these 2 conditions, they compete with each other. So especially if we take R0 to be small, because it's very difficult for Schwarz function to be somehow essentially like negative on almost all the Euclidean space, and for its Fourier transform to be simultaneously positive. And so what they've proven is that if we are able to construct this function for some real number R0, then we know that the sphere packing in dimension Rd has density, which is at most the volume of a ball of radius R0 divided by 2. And so here, of course, to prove meaningful and strong bounds on sphere packing, we're interested in taking this number R0 as small as possible. And so Kohn and Elkis, they have applied these bounds in many dimensions. For example, in the original paper, they went through to dimensions from 3 to 36. And in later papers, of course, also the higher dimensions were considered, and they found this for like in each dimension, they found for some R0, they found such a function, auxiliary function f numerically, and in all dimensions, they were able to prove some bounds and improve on existing bounds. However, in 2 dimensions, the result they got were surprisingly good. So namely, this happened in dimension 8 and in dimension 24. And so these are the numbers they got from their original paper. So they show that if there exists some packing in dimension 8, which is better than the E8 lattice packing, then it can be improved only by this small number. And say similar thing happens in dimension 24. Here, of course, numerical data is a bit worse, but also computation is more difficult. But one thing I should say is that these numbers, they were just the state of art in 2003. And since from after 2003, these numbers were improved significantly. And I think by the 2016, the best numbers that could be obtained here, they were about 1 and then 60 zeros. So it was clear that this is just a numerical error, and actually this one, it should be, this number should be replaced actually by 1 in both cases. And so this is the theorem I proved in 2017, is that indeed there exists a Schwarz functions FE8, which satisfies the condition of the theorem of Kohn and Elkis with the optimal possible value of R0. And then working together with Henry Kohn, Abhinav Kumar, Steven Miller, and Danilo Radchenko, we were able to prove all the similar theorem for dimension 24. And this time we proved it with optimal possible value of R0, which is 2 in the case of E8 lattice, of Leach lattice. And so now, how is interpolating formula useful for us? So let me show you the plot of my magic function. So this is how the magic functions or the auxiliary functions from from my theorem look like for dimension 8. And so we call this auxiliary function a magic function because it magically proves a difficult theorem for us with very little work. So all work has to be put into finding the function, and then we are saved a lot of geometric considerations. And so as you see at this function, so maybe there are certain aspects of function we can see from the plots. So first, that this is a radial Schwarz function. So it's essentially the theorem requires from us to find the function of 8 variables, but we can find this function, but we can safely assume that the function is radial. And we can assume it because all conditions of the theorem of Kohn and Elkis, they all rotation invariant with respect to rotation around origin. And so if we find one function of 8 variables, we can just average any rotation of this function around origin also satisfies the theorem. And we can consider the average, and then this would be a radial function. And working with radial functions, of course, is much easier than working with variables of 6, with functions of 8 variables. And another thing, we can see that our function has many zeros and even double zeros at all square roots of even integers. And this is not a coincidence. This has an explanation. And so here the explanation is again the Poisson summation formula. So imagine that we have this magic function which satisfies all the conditions of Kohn-Elkis theorem. But then, of course, this is a Schwarz function, and it also has to satisfy the Poisson summation formula associated to the E8 lattice. So here's this formula in the middle. So now what we are doing, we are applying the inequalities from Kohn-Elkis theorem, and this way we can estimate the sum from above and from below. And then the last condition in Kohn-Elkis theorem tells us that this value equals to 1 and this value equals to 1. And it means that here, when we are do these estimates, all the terms in the sum we have neglected, they all have to be 0. Otherwise, we could not get 1 and 1 on both sides of our estimate. And so this can happen if and only if our function and its Fourier transform, they vanish at all square roots of even integers. And because our function is a Schwarz function, and because it satisfies inequalities, we know that this vanishing has to happen up to second order. So same thing happens for the derivatives. And so now at this point, we already know, we know a lot of information about our function. We know information about its values at square roots of even function of even integers, same information about its Fourier transform, and we also know its derivative at this point, and same information for its Fourier transform. So now we can just apply our Fourier interpolation formula to this function, and then what we get is that our magic function f8, it has to coincide with b1, which is the the first element of the second order interpolating basis. And because I already told you that we have explicit formula for this function b1, now we can indeed check that verify that this function satisfies all the conditions of the Kohn-Elkes theorem, and this way solve the sphere packing problem. And so I think I would stop at this point. And if you are interested in 3 other applications, then I maybe can speak a bit more about this during your while you are also asking your questions. Maybe this would be a reply to one of your questions. So thank you very much.
Questions, comments?
Could you make a comment on how this is related to the conformal field theory?
Yes, did you hear? How is this
okay, so here maybe this most difficult question, because I'm not a specialist in conformal field theory, but what can I tell you that this is an interesting recent work by Dalimil Machak, and he also hit like a team of physicists working with him. And so here it works in the following way. So if certain types of conformal field theories, they produce an invariant very similar to theta function for lattices. So namely, if you have a conformal field theory which satisfies all the axioms of conformal field theories, then from it we can compute an invariant. And as I understand, this is the one which is called the partition function. And for a certain type of conformal field theories, this partition function, it has to satisfy, for example, certain symmetries similar to the symmetries of theta function of a lattice. And therefore, we would also have an analog of Kohn-Elkes theorem only applied to these partition functions. And then also the construction of auxiliary function will give us certain bounds on possible energy levels in this conformal field theory. So this is one possible connection. But then, of course, I think all the methods of what in mathematics, what we call linear programming and semi-definite programming, these methods are also used to somehow bound or to understand the spectra which appear in conformal field theories. And I think there this method has a different name called the conformal bootstrap. And I guess both are in many senses, they are different, but there is a very big intersection between these two fields. And so this, I think this is the connection, is that methods, somehow we are aiming for solving different problems, but methods we are used are very, very similar.
So any thought on sphere packing problem in other dimensions?
Of course, it's an active area of research, and I think from time to time there are new papers when for example, new versions of Kohn and Elkes theorem are proven. So it's clear that Kohn and Elkes theorem is a very nice result, but it will not be so if you want, for example, to prove sphere packing, to solve sphere packing problem in dimension 4 or in dimension 5. It's not strong enough. We need stronger methods. And so, but I think right now we are still even far away from getting very close numerical results. Right now, we still have this rather like measurable visible gap between examples and bounds. But of course, our crowd of mathematicians and computer scientists interested in these kind of questions, we keep working. And of course, we would be very interested to find, maybe the dream would be to find some universal, a very powerful method that can solve, so to say, sphere packing problems on a regular basis, because right now we can work only with some special dimensions. And I think that's not very satisfactory.
To continue that question, do you expect magic in some similar problems like Kapatiansky-Levenstein bound?
Yeah, so Kapatiansky-Levenstein bound, it's a very different type of bound. It's an asymptotic bound. So yeah, so if of course, I don't know, I believe that all mathematics is very beautiful and very magical, and even I think the paper of Kapatiansky and Levenstein, it's a beautiful paper. At the same time, it's very difficult to for example, what there is a paper of Henry Kohn and I think I don't with another yet another co-author from China whose last name unfortunately I don't remember. So what they showed that, for example, Kapatiansky-Levenstein bound can be proven by Kohn-Elkes method for a suitable function. At the same time, the way to construct this magic function, asymptotic magic function, is actually at the moment is to take the work of Kapatiansky-Levenstein, and from their auxiliary functions they produced, apply certain manipulations to it, and from it produce okay, would be not a Schwarz function, but a function in Euclidean space, which is has sufficient regularity for Kohn-Elkes method to work. And what we don't have at this moment is some kind of even for the Kohn-Elkes method. So there is also a recent paper of Henry Kohn with physicists where they numerically search for the best function, the best magic function in high dimensions. And it seems that there is a hope that, for example, there is a function which is there are functions which are asymptotically better than Kapatiansky-Levenstein, and surprisingly enough, this asymptotic improvement is very small. But at the moment, we think we don't have a systematic way of producing such functions. So in this sense, of course, there is a lot of space for new beautiful ideas. So.
Okay, thank you. And okay, one more for me. Again, kind of continuation. Do you think that some magic can be done in SDP, same definite programming? Maybe this is one way to find better power.
Yes, I think we should go to some kind of so we like this well, maybe SDP or working with some more general like subcons inside of this con of copositive functions. And yes, I think in SDP it could happen that we again have making like reducing our problem to some like to some so after like finite depth of SDP, because SDP has this like natural hierarchy. In SDP we have to consider semi-definite matrices, and somehow the size of matrix is fixed. And yeah, so maybe for some fixed number of matrix we again get sharp bound, and I would see this some kind of again like analog of this magic coincidence, because a priori it's not clear that after like considering only finite size of matrices is sufficient. It can happen that sharp bounds require in some sense infinite like infinitely large matrices. But yeah, but here I think maybe at least well, from what I know, numerical data is maybe not good enough. So there is some hope for a kissing problem in dimension 4. So there somehow the kissing number is already found, and it's found by essentially by SDP method. So the proof of Musin, it is I think in a heart it is SDP, only formulated in a different way. Then there is a alternative proof by Christine Bachok and Frank Valentine. And I think people who work in this area, they do believe that at least we can take only finite size of matrices. And for a finite size of matrices, we could find this exact, to find a bound on the kissing number, which is not like 24.9, but rather sharply 24. And this could be an indication that something like this also happens in dimension for packing problem in dimension 4. But as I know, the numerical data is not good enough in dimension 4 to make that conclusion. So we don't have this striking result like the result of Kohn and Elkis, where we see that this numerical error is so close to 1, and that we really caught this correct phenomena. I think that in dimension 4, we are still not there, but I might be wrong. So maybe, yeah. Maybe somebody has already made that computation, just waiting to publish the paper.
A distinct long way from numerics to analytical expression.
Yeah, so there's also my my information is that we are still quite far away. And then of course the question would be, why are we far away? Is this a computational problem, or is just the essential property of this method? Maybe just the method does not get that close. But here, to be honest, I don't know.
Okay, thank you. Some other questions? Okay, fine. Let me give credit. I just realized that result of Kohn-Elkis was also proved by Gorbachev, Dmitry Gorbachev, but he published in some journal of Tula University, so not so popular, but it was independent.
Yeah. Thank you. So I think it's a mistake I often make. Maybe just because when I was working on this, I mostly worked with a paper of Kohn and Elkis, and at some point I even tried to find the paper of Gorbachev, and it turns out to be, it's not an easy thing to find it even now.
I found it many years after I saw Kohn-Elkis.
Yeah, so that's. Yeah, but maybe one thing I should also say that, of course, this method of linear programming, many people work on that, and many people contributed, and I mentioned mostly Kohn and Elkis because their paper, it was the reference I used the most. But yeah, but it was actually a big work done by many people, and also Gorbachev was a person who found essentially also an analog of Kohn-Elkis theorem around the same time independently.
Okay, thank you again. I hope to see you indeed in Sofia soon.
Yes, I hope, yes.
Bye.
Thank you.
So let us start the second talk of our morning session. Talk by Liana David from Institute of Mathematics of Bulgarian Academy of Sciences. The title is Beyond Generalized Pseudo-Carrier Structures.
First of all, I wish to thank the organizers for giving me the opportunity for inviting me and giving me the opportunity to give a talk at this very nice conference with such big names around. So the title of my talk is this, Beyond Generalized Pseudo-Carrier Structures. And I'm going to present a joint work with my collaborator Vicente Cortez, which we put on the archives very recently. So in the first part of the talk, I will recall some known results about, I will recall what a Courant algebroid is, what are the odd exact Courant algebroids, which is going to be the main structure I will consider in this paper. And then some definition and some results I will need about generalized structures, namely BN and generalized complex structures, which were introduced by Roberto Rubio in his PhD thesis in Oxford in 2015, and generalized metrics, which are more commonly known. And then I will pass to the new material which I want to present, namely the definition and basic properties of these structures I'm going to introduce, being generalized pseudo-planar structures, and I will give some examples of Lie groups in small dimensions. So the computations are quite involved. So this is just a very brief summary of our common results, but for someone who wants to see the details, I mean, the paper is on the archives. So let's see, what is a Courant algebroid? So a Courant algebroid over a manifold is a vector bundle endowed with several structures. So the first one is a non-degenerate symmetric bilinear form. Some people consider it sometimes to be of neutral signature, but in general, I mean, the definition does not require this. A bilinear operation on the space of smooth sections of the vector bundle. This is not necessarily symmetric. And the homomorphism of vector bundles, which is usually called the anchor, which are subject to these constraints. You see, the Dorfman bracket is not skew symmetric. Its symmetric part is measured by this last relation. Right. And the first example is the generalized tangent bundle. So if you consider the direct sum of the tangent and cotangent bundle.
Sorry, could you go back to the previous grid? I'm sorry.
Yes.
So is it the first condition, the Jacobi identity or not?
Well, you may see, well, it's some kind of derivation. Or
yeah, just to note, so it's not completely because it's not anti-symmetric, so you cannot make it in this usual form. Yeah, so it must be like this.
yes, it's, yeah. So the first example is the generalized tangent bundle, which is a direct sum of tangent and cotangent bundle with the anchor. So I had here the anchor, the natural projection, a projection from the bundle to the tangent bundle. The anchor is a natural projection. We have this scalar product, which in this case is a mutual signature, and the Dorfman bracket defined in this way in terms of a tree form which should be closed in order to have all the compatibility conditions which are expressed on my last slide satisfied. And these such Courant algebroids are called exact, and they are the underlying setting for the so-called generalized complex geometry, which was introduced by Nigel Tichin and Gualtieri, who used these exact Courant algebroids in order to unify complex and symplectic geometry. So more precisely, they noticed that a complex and symplectic structure can be unified into a type of structure which consists of certain endomorphisms of the generalized tangent bundle. We satisfy certain properties, and these were called generalized complex structures. I didn't write it here, but probably I should say that, let's say J is a generalized complex structure. If J is an endomorphism of this generalized tangent bundle, which is skew with respect to the pairing which I wrote on the previous slide, which satisfies its square is minus the identity, and moreover it should satisfy an integrability condition, namely that the space of section of its I eigenbundle is closed under the Dorfman bracket. And then you see immediately that if you have a complex structure, you can define such an endomorphism in this way of the generalized tangent bundle. And if you have a symplectic form, you obtain also a generalized complex structure, and this integrability condition reduces to the integrability of the almost complex structure, and to the fact that the form omega is closed. So this is really a unification of complex and symplectic geometry. So this was the starting point of the theory, but then later on, other structures from classical geometry were extended to this generalized setting under the same, using the same recipe by replacing the tangent bundle with a generalized tangent bundle. So in particular, there is a notion of generalized scalar structure, whatever this is. I'm not going to define it here very carefully, which received a lot of interest also because it is related to B-Hermitian geometry. And here I will only recall the formula. So generalized scalar structures. Generalized scalar structure, let's say I will denote, so I will on the generalized tangent bundle with a Dorfman bracket twisted by a closed form, a closed free form. They are shown to be in a relation with B-Hermitian structures of a certain type. So namely B-Hermitian structures, so G, J plus, J minus, and B. So here we have a Riemannian metric. G plus and G minus are skew-symmetric integrable complex structures. And here B is a two-form. B is a two-form. And such that certain connections, which have the additional properties that the following connections, nabla x plus minus 1 over 2 h plus db preserve, so this preserve G plus minus. Nabla here is a Levi-Civita connection, and H is a three-form from which on which the corresponding generalized scalar structure was defined.
Sorry,
And
what is it? This is nabla x or plus minus?
Plus minus 1 over 2, applied to x, yes, applied to x.
Just go.
Yes, applied to x, so I identify vectors and covectors by means of...
But what is written after the h?
dB, the exterior derivative of the two-form B.
Oh.
So this is a three-form. And by means of the so-called B-field transformations, in fact, we can forget about this dB and obtain B-Hermitian structures which are preserved by such connections. And without, we can forget this by making B-field transformations. This is a notion in generalized geometry. I will not explain it here. It's not so relevant. I will come back to these expressions. And the purpose of my talk, our results are that we obtain similar conditions, but in a different, starting with a different Courant algebroid, not necessarily an exact one. So I should mention that this field is received a lot of interest, and there are many mathematicians working on it. I cite Vestislav Apostolov, Grancharov, because we are in Bulgaria, and also many others, Cavalcanti, Anna Fino, Henrik Burstein, and Susan Tolman, and so on. So a natural question is, can we develop a generalized geometry on other Courant algebroids? And for this, it is, first of all, the first question is, can we classify, or how can we feel better these, the Courant algebroids in general? And there is, in fact, there is a classification result by these authors, Chen, Stienon, and Xu. It appeared in Journal of Symplectic Geometry, who proved that up to isomorphism, in fact, any Courant algebroid has a very close form to the exact ones, except that we have here a new bundle with some new structure. So I said here transitive. Transitive means that the anchor is a subjective map, but the result is more general. It refers to regular Courant algebroids. it's simpler to state it for transitive. So they prove that up to isomorphism, any Courant algebroid is of the form, so the underlying bundle is the generalized tangent bundle as before, plus a new vector bundle, which is a quadratic Lie algebra bundle. So in particular, it has a Lie algebra structure in each fiber. It also has a non-degenerate metric, which is ad invariant. And so this is a new structure which we have. The anchor is a natural projection to Tm. So as before, as we had for exact Courant algebroids, the scalar product is as before plus the metric plus the scalar product of this additional bundle. And the Dorfman bracket, well, in order to define the Dorfman bracket, you need more structure. Namely, you need a connection on this bundle, a 3 form, and a vector value 2 form, all of them satisfying certain compatibility conditions. Well, these definition of these structures just come from taking a Dorfman bracket on here and projecting it onto the components. For example, if I want to explain how I define the 2 form, I just take x and y, two vector fields. I take the Dorfman bracket, and then I project it to the bundle G. And the compatibility conditions which define the Courant algebroid translate to certain compatibility conditions between all this data. And then you might think, well, let's consider the simplest class of non-exact Courant algebroids. So this would be, if we take G, the vector, that bundle G, to be just a trivial bundle with a trivially bracket, with a canonical metric, and with a canonical connection. And applying this receipt we obtain, we can write down the metric. So we obtain a class of Courant algebroids which were called by Rubio in his PhD thesis of type Bn. So Rubio was, as far as I know, the first mathematician who considered such structures. And so he defined a Courant algebroid of type Bn as being one for which the scalar product is given in this way. It is precisely what we had before with here the metric, the Santa metric. Dorfman bracket given in this way. So end with the, I think I forgot to end with the anchor, the natural projection. So we are left with a 3 form and with a 2 form. In this case, the 2 form is not anymore vector value. So it's a 2 form. And the compatibility conditions, which I did not write on this slide, they reduce to this equation.
What does the n, the subscript n represent?
Yes, n is the dimension of the manifold M. And yes, you may ask why is it of type Bn? Because if you look at this scalar product, it has signature n plus 1 n. And then he said, for this reason, he introduced this terminology. From this point of view, you may see the generalized tangent bundles Tm plus T star m as being Courant algebroids of type Dn because the scalar product is of neutral signature n. So here, yes, indeed. So n is a dimension of the manifold. Right. And the Courant algebroid is called odd exact if it is isomorphic to a Courant algebroid of type n. So what is known about generalized structures on odd exact Courant algebroids? So Bn generalized complex structures were introduced in Rubio's thesis. So I'm going to recall the definition and certain properties which I'm going to use. And generalized metrics, well, generalized metrics already received much interest on other types of Courant algebroids, not necessarily on not necessarily on the generalized tangent bundles. They were considered in connection with T-duality on a class of Courant algebroids which is called heterotic Courant algebroids. So So these were introduced already for any Courant algebroid by authors like David Baraglia, Hekmati, and Mario Garcia Fernandez, so by many other authors. Okay, so let's recall these structures. So let us consider an odd exact Courant algebroid over a manifold of dimension n. With scalar product, I fix it in this way, Dorfman bracket and anchor denoted by this.
Sorry, may I just if you go back to 2 slides or 3 maybe. So this is a theorem that there is this like, so if for exact Courant algebra we have this Chevreul's classification by 3 forms. So this is also.
This is a consequence.
This is a consequence of this.
Of that.
Yes, okay.
It's just the application of that general classification theorem to the simplest case.
Okay.
But of course, I mean, you can verify by hand that all conditions are satisfied.
Yeah, but I meant more like if you take you define it as isomorphic to this.
No, I just say, well, I just gave a motivation for this bracket because I could have started from here, say that I could have said, well, I defined such a Courant algebroid, and then you may have asked me why did you have this? Why did you define the Dorfman bracket in this way, not in another way?
Yeah, I guess my question was more like, is there like an intrinsic definition in the, like for exact Courant algebroid, you have this exact sequence, and then you prove that all of them look like Tm plus T star n, which is not a priori clear.
Yes.
So if there is also interesting definition of this.
I think Roberto is doing such thing in his theories. Maybe we should.
Okay. Thank you. Yeah.
Can I ask you some simple question? Is it this bracket skew symmetric?
No, it's not symmetric. No, I mean people work with yes, many people work with Courant. So instead of Dorfman bracket, they work with Courant bracket, which is a skew-symmetric part of the Dorfman bracket. So you might work also with Courant bracket, and in that case you have skew-symmetry, but here you don't have skew-symmetry. Okay, so now I recall what, I will explain what Bn generalized complex structure is. So it is just a maximal isotropic subbundle which satisfies this relation. And well, it is this is a Bn generalized almost complex structure, and you have the integrability condition, namely that the space of sections is closed under the Dorfman bracket. And then from the maximality, you see that the scalar product restricted to L plus L bar is non-degenerate. And then you can consider also its orthogonal complement with respect to the pairing of the Courant algebroid. And Rubio shows that this orthogonal complement is generated by a real section which can be normalized in this way, where I record that n is the dimension of the manifold. But since we are used to see complex structures and so on as endomorphisms, so there is a relation. We can also define such a structure in terms of endomorphism, namely by we define an endomorphism F by this formula, and we see some of its properties, namely that this is a skew-symmetric endomorphism. It has, of course, kernel that and satisfies that relation. So we could have defined a Bn generalized almost complex structure as an endomorphism of E satisfying these properties, where U0 is a section, an arbitrary section of E, which is normalized in this way. Maybe I should say that there is what lies under the algebraic setting, which lies under the generalized complex structures, is related to the representation theory of the group SON plus 1, 1. So you could have said so there is a Clifford action on there is an action of the Clifford algebra, Clifford TM. plus T star M plus R acts on the bundle of forms by the followed by x plus psi plus lambda applied to omega is equal to Ex of omega plus psi wedge omega plus lambda multiplied by tau of omega. So where tau of omega is equal to omega plus minus omega minus, we have, this is an element of Tm. So this belongs to Tm plus T star M plus L. And so you can define generalized complex structures in terms of, so the bundle of forms becomes the bundle of spinors, and you can define generalized complex structures in terms of the corresponding pure spinors in the usual way. So you have some pure spinors, which are sections of this complexified bundle, and then the corresponding null space. I will not enter into this, but then the corresponding null space is the bundle L, which defines a generalized complex structure. So there is this theory, which is very analogous to what is known in the exact case. This is just I wanted to recall this very briefly.
Sorry, may I just ask you so that I understand? So the previous slide. So do I understand correctly that this almost complex structure is not just an endomorphism which squares to -1?
No. It should satisfy this relation.
But isn't this? So why is not this definition meaningful? To square equals -1.
Because the rank of the bundle. So n has a rank
so
2n plus 1.
Yes.
It has rank 2n plus 1. Now, following Baralia, Hekmati, and the other authors, we define an admissible generalized metric on E as a rank n vectors bundle with a property that the restriction of the metric is non-degenerate and the restriction of the anchor is an isomorphism. And we see that there is an induced pseudo-Riemannian metric defined in this way, so there is an induced pseudo-Riemannian metric defined in this way. In the case when the metric is negative, the restriction of the metric to E minus is negative definite, the admissibility condition is automatically satisfied. So from now on, I wrote here in parentheses because I will assume that all generalized metrics which I will consider are admissible.
Excuse me, what is S?
S is the inverse of this map, this restriction. Yeah. And now we have a simple lemma which says that if we consider it a Courant algebroid of type Bn, so in the standard form, which I presented at the beginning of my talk, then modulo BA transformations, it takes this form. Let's see very quickly what is a BA transformation. This is the analog of the B-field transformations from the classical geometry. So, namely, if I have a 2 form on M, together with a 1 form on M, then I can define an endomorphism 0, 0, 0, B 0 minus 2A, A 0, 0, which is Q-symmetric, with respect to the pairing which I introduced before. And then, if we denote this by, let's say, B plus A, and then the BA transformation is the exponential of this. And one can show precisely like the B-field transformations from the usual, from the generalized tangent bundles, one can show that this behaves nicely with respect to the Dorfman brackets, namely that we have a relation of the form X of, let's say, B. So BA, U, B, A, V. Dorfman bracket with respect to some H and F, to some Dorfman bracket defined by a couple F, A, and F, is equal to BA, BA applied to U, B, a Dorfman bracket with respect to another pair of forms H tilde, H tilde, F tilde. So what this says is that these BA transformations map Courant algebroids of type Bn to Courant algebroids of type Bm, but twisted with different pairs of forms. So this lemma says that modulo such a transformation, we can always map generalized metric in this simple form. So here, this is just a pseudo-Riemannian metric of M. And now, I will start the part which is new. So we define the notion of Bn. So we define scalar geometry, generalized scalar geometry, in analogy with the generalized scalar geometry on the generalized tangent bundles. So namely, we said that a Bn generalized pseudo-Hermitian structure is a pair formed by a generalized metric and a generalized almost complex structure, which should satisfy a certain compatibility condition, which is this one. So we notice that this is precisely the compatibility condition which enters into the definition of generalized scalar metrics on generalized tangent bundles. So this Gn is an endomorphism of E, and which is defined by this relation where E plus is the orthogonal complement with respect to E minus. And this condition is just written in the equivalent way, like that. Right. And now we recall that a generalized complex structure had a particular section in its kernel, normalized in this way, and one can show that, well, this section belongs either to the bundle E plus or to the bundle E minus, depending on the dimension of the manifold, if the dimension of the manifold is even or odd. And the integrability, we define it as so first of all, we notice that this composition is also a generalized, a Bn generalized almost complex structure, and the integrability is defined by imposing integrability on both F and this second Bn generalized complex structure. And now we look at components. So now I will come back to my first blackboard and see how these generalized complex structures, generalized pseudo-scalar structures translate into classical structures of the manifold. So we start with a Courant algebroid of type Bn. We consider a Bn generalized almost pseudo-Hermitian structure. Without loss of generality, we assume that the metric is given by this way, in that way. And now what we obtain is the following. So in the generalized, in this setting, in the classical setting, we just had two complex structures, integrable, preserved by these nice, quite simple connections. Here the situation is a bit more complicated. So we obtain that a Bn generalized almost pseudo-Hermitian structure is equivalent to this, where we have a pseudo-Riemannian metric. We have two endomorphisms which are skew-symmetric, two vector fields which lie in their kernel, and such that the endomorphisms restricted to the orthogonal complement are complex structures, and these two are also should have norm 1. And so the proof is quite simple. So maybe it looks a bit complicated, but in fact the proof is not so complicated. We just look at the bundles E plus and E minus and E plus, and we project the endomorphism F, and we obtain some data, precisely that data base. So by means of this natural isomorphism, so we have this natural isomorphism, we have that the pairing induces a metric, the restriction of the complex of the generalized complex structure induces J minus, and U0 induces G plus. So we already have the metric, we have G minus, we have X minus, and the properties they are very simple. One can check them directly. Let's see how we define. So we still have to define G plus and X plus, but they are defined. In this way. So first of all, we notice that X plus, E plus is given in this way. So there is a natural isomorphism between E plus and this bundle. And again, we consider the almost complex structure F restricted to E plus. It will induce an endomorphism here. And writing the endomorphism in terms of components, we obtain what is missing. We obtain G plus and X plus. So I explained how.
Sorry, what is the integrability condition?
I haven't. This is only algebraic. So I considered only for the moment. I will go to the integrability condition, but for the moment, this is just everything is only algebraic. The integrability condition is this one. So we define connections on Tm by this formula. So these are the analogs of these connections. Here we identify forms and tangent vectors by means of the metric. Nabla is again the Levi-Civita connection. And so the pair is integrable, so we have this integrability result, namely these two connections preserve. So this is a bundle, this is the I eigenbundle of J plus minus. They should preserve, so Nabla minus preserves X minus, and we have this relation, and some other algebraic constraints on which were quite a bit longer, so I didn't write them on the blackboard. So there is clear similarity between what we had for generalized tangent bundles, but of course here the conditions are much more complicated.
Excuse me, I'm confused. I read somewhere N odd.
N odd, yes.
So
I will.
So how can it be M has odd dimension and you have these?
Yes, J plus minus. So we don't have. So N is odd. J plus and J minus. They are not complex structures, of course. They so they emulate X plus minus.
Yes, but the notation to say
the notation, yes, the notation just means that it is an I eigenbundle.
Okay.
This is.
Is it related to CR geometry?
We haven't studied that. I saw some paper by Grandini and someone else who claimed, so you consider the CR geometry in the setting of generalized geometry, but it's not that they didn't arrive. But I don't remember right now what they did. But in any case, we didn't investigate this aspect. Yeah. So. Right. So that was for n odd. Now for n even. So for n even we have. So what's the difference between odd and even? For n even we have an additional function which comes. So the main difference is the fact that that section U0, which lies in the kernel of F, is either a section of E plus or a section of E minus, depending on n odd or n even. When if it is a section of E, if n is even, then it is a section of E plus, and E plus was isomorphic to Tm plus R. So corresponding to U0, we had a vector field and a component on R, and this component, the component of R is this one. So we have here this additional data. So this is purely algebraic. In the case when n is even, we obtain such a structure on the manifold. Namely, we have a pseudo-Riemannian metric. We have two endomorphisms, two vector fields, and a function which should satisfy these compatibility conditions. And again, the proof is very simple. It's just we look at f restricted to E plus and E minus. And we project it via the isomorphism between E minus and E plus. We obtain the tensor fields on the manifold.
Can I ask you?
Yes.
So, can you say about the automorphism group of this algebraic structure?
We have, the paper is not, conceptually the paper is very simple, and it's, I think, well, it's the obvious thing to do once you know what's happening in the classical generalized geometry. So when the Courant algebraic is Tn plus T star m, but the computations are quite ugly and nasty. No, we didn't have neither place, no energy, and no time to include such questions here. Yeah.
But do you have some obvious automorphisms similar to what you have in the GC case, like different morphisms, B fields plus an extra piece that corresponds to one isotropic direction?
No, we haven't. No, we just arrived. We haven't thought further than this, then obtaining these and then looking for examples. Yeah. And the integrability is the following. So again, we have these the two connections. Again, they are more complicated with what we had before. And the integrability is stated in the following way. So again, we use this notation which may be confusing, but always, so it refers to the I eigenbundle of G plus minus. So in the case when n is odd, n is even, we have integrability is equivalent to these conditions. I don't know, how much time do I have?
20 minutes.
20 minutes.
Yeah.
Okay. Now, the proof of integrability follows, is very similar to the proof by Gualtieri in his PhD thesis, but it's based on a remark, again, of Roberto Rubio, which noticed that, in general, if we have a Bn generalized complex structure, then the Dorfman-Lie derivative with respect to that particular section in the kernel of F, normalized in that particular way, preserves the bundle of preserves the space of sections of the corresponding bundle L. And then, so the proof of integrability, it goes in this way. So we consider, so let's consider L1 and L2, the I eigenbundles of F and the other almost complex structure. And we show that, well, this is integrable. In the first step, we show that integrability is equivalent to the Dorfman integrability of these spaces of sections, together with the fact that the Dorfman-Lie derivative with respect to this particular section preserves this intersection. And in a second stage, we just express these intersections in terms of the components, in terms of those tensor fields on the manifold, and show that the above conditions written in terms of components give precisely the conditions which I wrote on the blackboard before. So it is very similar to what Gualtieri does in his thesis. The more ingredient and the key ingredient here being this section. So here we have an additional condition, the fact that the Dorfman-Lie derivative preserves that intersection. I could also write down how. So if let's see how. give an idea, when n is odd, let's say when n is odd, then L1 intersected with L2 is equal to x plus g of x, where x belongs to T1, 0, g plus n, plus r of x plus g of x plus I, and L1 intersecting with L2R is equal to x minus g of x when x belongs to g minus 1, 0 of n. We have such, and when n is even, we have similar expressions. Okay, so now let's go to examples. So left invariant examples. If we consider a Lie group with Lie algebra G, then a Courant algebroid is called a left invariant. If the Courant algebroid of type Bn is called a left invariant, if the three forms, if the two forms H and F are left invariant, and the generalized pseudo-Kähler structure of type Bn is left invariant, if all the tensor fields are left invariant, if the components, so the tensor fields which we obtained on the Lie group are left invariant. So with this, everything translates into an algebraic question, and we look at dimension 2, 3, and 4. And so, unfortunately, when G is two-dimensional, then the existence of a left invariant pseudo-Kähler structure implies necessarily that G should be abelian. But in the dimension 3, we already have examples on the non-abelian Lie groups. So there is a left invariant example on a Lie group of dimension 3, if and only if the Lie algebra of G is one of these semi-direct products, or the direct sum of R plus the two-dimensional non-abelian Lie algebra. And then in dimension 4, well, in dimension 4 we considered a particular class of generalized pseudo-Kähler structures which we called adapted, and we again we found the form of the Lie algebra, which ensures that generalized pseudo-Kähler structure exists. Let me see what it means adapted. Well, we introduced the notion of adapted only because to simplify computations, because the computations became quite hard. So we said that, so fix a four-dimensional Lie group with Lie algebra G, fix left invariant before generalized pseudo-Kähler structure with the tensor fields, so with the components in this way, and we assume that G is of this form. Well, this is a three-dimensional Lie algebra, I forgot three-dimensional non-abelian Lie algebra, and U acts as a one-parameter family of derivation of G0. And the definition is that, a generalized pseudo-Kähler structure is adapted if and only if, so it has several conditions. The restriction of the metric G to G0 is not degenerate. The above decomposition is a G orthogonal. The operator L, I will explain what is the operator L, is diagonalizable. I will explain it later. And we have this additional condition. So this operator L was introduced for the first time in a paper of Milnor in 1976. On N it relates the Lie bracket with a cross product on any three-dimensional Lie algebra which is endowed with a metric, a non-degenerate metric and an orientation. So it is defined in this way. And Milnor proved that when the metric is positive definite, the Lie algebra is unimodular if and only if L is self-adjoint. This result was recently generalized by Vicente Cortez and his PhD student David Fuchen to the case of indefinite signature. And so in the case where, so this condition diagonalizable is automatically satisfied when the restriction of the metric is positive definite, and when this G0 is unimodular. And now I mean just an example, explicit example. For example, I wrote it down here. I considered only the case, I considered only this situation, is the Lie algebra being given by such semi-direct products. And you can see here that you can write down the form of the Lie bracket, and in an orthonormal basis of G, and also the vector field x minus x plus and everything. What is still what we didn't like, but all our examples were obtained for the untwisted case. So it turned out in all these small computations that H, the 3-form H and the 2-form F should be 0. Vicente is convinced that this is only matter, it's a consequence of the fact that we considered only very small dimensions. So we are looking for further examples in which the dot bracket is twisted. So H or F, not necessarily. I finished.
We had many questions during the talk. Some more questions? Yes?
Yeah, I have one question. So in the general scalar setting, these durability conditions are overdetermined this holomorphic structure. If you take the commutator of like initial complex structures, multiplied by the method, you get a Poisson tensor. So did you try to say this is
So say again, when you hear?
So in the classical case,
The classical case, yes.
general scalar,
Yes,
the durability conditions
Yes.
are overdetermined.
yes.
And the overdeterminacy is expressed by this holomorphic Poisson tensor.
Ah,
So
yes.
you tried in your setting
No,
to see.
no, in fact, I didn't know this statement even in the classical case. So what is it?
It
Where
probably is
can I
interesting
find
to
it?
look at the examples.
Where can I find it?
Oh, it's a result of teaching in 2006.
2006. In a paper or?
Yeah, but I can.
No, I mean, we will try to write this integrability condition in the most appealing possible form, you know. But still, they are quite complicated. But the next thing we have to do is to find examples when at least H or F are non-zero.
Please.
Have you tried some symmetric spaces or homogeneous spaces?
No,
We have a lot of
no.
symmetry in
No, but we intend to come back to this question. So there are things which are not finished. Another thing related to this is to look at Kähler-Einstein, generalized Kähler-Einstein matrix. So there is this notion of a Ricci tensor can be defined for any generalized metric on any Courant algebroid. And then we want to impose, to try to classify the generalized scalar structures, which also satisfy the additional condition that the Ricci tensor is 0. In fact, Vicente just put a paper on the archive very recently, in which he and his PhD student, they classified left invariant Einstein generalized metrics on three-dimensional liquids. So they found, and then we can ask, I mean, if we can add. So there are these questions later.
One more
Well,
question.
so you were talking about these Courant algebroids, but are there generalized complex structures or these structures defined for other like?
I haven't seen it in the literature. Generalized metrics, yes. Generalized metrics, you can look at heterotic Courant algebroids, and there are lots of physics literature, and in particular there is this paper which I already mentioned by Baralia and Ekmati, where they look at generalized metrics and Ricci tensor and T-duality and so on, and other physicists. But no, I only saw for these type of Courant algebroids the notion of generalized complex structures, only for these old exams, either by the work of
Yeah, I'm wondering, like, how do you know that this is the correct definition, or I mean, because.
Well, how do I know?
Yes.
Of what? Of everything.
Yes, it's like,
No, but well, once you start and if you assume that it's, if you take it, if you think it's reasonable to define BN generalized complex structure as a adaptive, the definition of BN generalized scalar structures is very natural because you look how it is done in the usual for Tm plus T star n. And now, I mean, if you think, I mean, to convince yourself that it is for generalized complex structures of type Bn, so what would you introduce? I think it's, well, it's...
For example, you know, there are these reductions of Courant algebroids that you can get from, say, like heterotic to exact. So I would be interested if you can, like, study the generalized complex structure on
upstairs and see what you get.
See if you get this, or...
Yes, it's a very good question, yes.
Yeah.
Yeah.
Okay. Yeah, please.
Are there some topological restrictions for the existence of such structures? Or if you want, do you have some examples that do not admit?
We have to, at least for what we did, I mean, we just arrived at this point.
Yeah.
But there are these, yes, there are many questions.
Okay. So let us thank again. So it's the morning session.
So the first speaker is Professor Julian Andersen from Center of Quantum Mechanics, Odense, and he will talk generalized hitching connections with application to consolidation of modular space of parabolic vector functions.
Thank you, Kenji. So, well, it is a Center for Quantum Mathematics, and not Center for Quantum Mechanics. But now in this talk you will see it's the same thing, more or less. Okay, so I think that what I will do is I will somehow give the second half of this talk in Sunny Beach. Okay, so I will skip half of this talk because else we won't get through it. But anyway, does this work?
Yeah.
No? Perfect. So what I want to start with is just set the general scheme for pre-quantizing a symplectic manifold. So you should imagine you have a symplectic manifold, and we say that that's pre-quantizable if you have the following cohomological condition on the symplectic form. It just has to lie in the image of the integer second cohomology inside the second real cohomology. So if that is true, then it's a very simple little argument to show that there exists a complex line bundle on M with a Hermitian structure and a Hermitian connection in that line bundle in such a way that the curvature is exactly minus I omega. And so such a triple we call a pre-quantum line bundle. So let us assume that that's the case, and then let's look at the Hilbert space that pre-quantum theory would like to give you. It is simply all the L2 sections of M. Sorry, of L over M. Okay. And so on that Hilbert space, there is very simple construction of quantization of functions. So the process of going from classical observables, which are functions, to operators. Well, of course, as usual in quantum mechanics, unbounded operators. But here you are as a completely explicit formula for the operator, and x lower f is the Hamiltonian vector field associated to the function f with respect to the symplectic form we have. So it's a first order operator we associate to every function. And these functions, they satisfy a perfect Dirac quantization condition that says that if you take the Poisson bracket of the two functions and you take the operator associated with that, that's exactly the commutator of those two operators.
So this is a covariant derivative?
That is the covariant derivative. So that's the same as this connection here. That's
okay, the same one. Oh,
yeah,
yes,
yeah.
yes.
Okay, so know where I should stand so you guys can see. Okay, so why is this not the end of that talk? You know, So the thing is that there are several complications with this. One of them is this does not reproduce canonical quantization. And canonical quantization is quantization of R2n in the way that physicists like to do this. And of course what they do is they choose L2 functions on Rn, so half the variables. And then they construct operators on that, and it really works very well with physics. I know that now, because I'm actually in Denmark working together with some people to try to build photonic quantum computers. And the thing they're using is canonical quantization, and it fits experiments extremely well. So it's not just a side remark. I mean, it really is true. Of course, also you will get violation of Heisenberg uncertainty principle if you do this, and so on. So really, there is a need for. Could you put the finger on the slides again?
The B is because of this relation, like why do you have the relation of Heisenberg?
Yeah, it's a. Sorry, I can't use this if you don't. I don't know what's going on. You should just think about it that the wave functions depends on both position and momentum. And so, you just simply can't, you will very quickly show that you can violate Heisenberg uncertainty principle. So it's essentially that's the reason. Does it work now? Thank you. All right. So therefore, what I will be focusing on is to pick the Kähler situation, the Kähler quantization, because there's already lots of problems that hasn't been solved fully in that setting. So I will pick an almost complex structure I on the manifold. So as you know, it's an endomorphism with tangent bundle, it squares to minus the identity, and it leaves omega invariant like this. And so if it is further integrable, then it makes it a Kähler manifold. Super. And so the condition is that it's a positive definite Riemannian metric when you do this G defined this way, combining omega and I. Great. So now I take this Kähler manifold, and now of course I have the option to look at holomorphic sections of the line bundle with respect to this complex structure as I do here. Okay. And if I want, I can also endow it with a Hilbert space structure, because I have of course the volume form from the symplectic form, and I can just take the pointwise norm of sections, and I can integrate them squared over the space, and I want this to be finite, that's a Hilbert space. So this one here has way better properties. It reproduces, if you do this for flat space, it will reproduce for you canonical quantization. Okay. But so there are big left, many problems left open here. So one of the
dimension has to be a multiple of 4, or
sorry,
no.
What?
Just even dimension. No.
Okay. So there are many things that are left open here in generality. Namely, how does this Hilbert space depend on I? That's one thing. And what should the real pre-Hilbert space structure be? And how do we quantize observable? Because if you just take this formula here, this formula does not preserve holomorphicity in general, so it will not act on this subspace of holomorphic sections. So we need to sort of figure out a way to quantize observables. And the classical theory of this really does not answer these questions. Well, the only thing that I've heard over and over again in this field is that quantization should projectively be independent of this polarization, of this complex structure. I think I want to really significantly sort of say, I don't believe this. I really don't believe this.
Why do you want the pre-Hilbert space to be the set of holomorphic sections?
Yeah, this is sort of, holomorphic is basically functions of half the variables. So what physicists does is they look at, P's and Q's. And the symplectic form, they then put in standard form dq weights dp. And so they're basically looking at Lagrangian subspaces and a vibration, and then they get their Hilbert space by taking functions that are covariant constant along half of the directions, which are in involution with respect to Poisson bracket. And the generalization of this is to look at a Lagrangian subspace of the complexified tangent bundle. And one of them is obtained by just taking I, because you can take the holomorphic tangent bundle inside the complexified tangent bundle, and that's Lagrangian on a Kähler manifold, with respect to the complex extended symplectic form.
Hollow condition is a global condition.
Yes, yes, that's a global condition in a manifold. It's just but described locally, right? Okay. But
So
it
in
needs to be.
that case, can you consider some Dirac operator instead of the global condition?
So we will get to what kind of operators that gives you and so on. But I just want to make a little bit of fuss here and saying, I think we need to rethink the situation. And I think that the quantization should really depend on what kind of polarizations you want to use and consider. But what I will do in this talk here is I will give you answers to 1, 2, and 3 for general symplectic manifolds that emit scalar structures.
I'm a bit confused about 2. I thought you told us on a previous slide what the hell.
That's right. But that I sort of said, one possibility is this one. But I will show you many more, just as good possibilities than this one.
Many more means you're changing the type of polarization, or you're changing the type of operators for the still the Kähler polarization?
All of them. Actually, you've seen that. Okay, so let's get started with some fundamental stuff here. So what I really want to look at is I want to look at a family of Kähler polarizations, and not just one. I want to take a manifold T, and then I imagine I have a smooth map from T into this vector space in such a way that for every point sigma and T, I get a Kähler manifold. So it's basically just a family of Kähler manifolds, all the same symplectic manifold, but I'm varying the Kähler structure on it. And sigma, so a little bit of a few things you have to remember. Sigma is a point in this parameter space, and the parameter space is called T. Okay. And so from what you can then see is that of course you get a subspace for each sigma, namely the holomorphic guys inside the smooth sections of L. And what I will be entirely doing from the rest of the talk is I will assume that that forms a smooth subbundle. So of course in general we know that these dimensions can jump, I mean for example if M is compact, it's finite dimensional, right? And this could jump up and down in dimensions, so there's no way I can hope to make that a bundle. So I won't consider the cases where the dimensions jump. I have answers to this also, but not for this talk.
Can you remind us why L should be holomorphic line bundle for every sigma?
Yeah, and that's simply because you just take the connection and you combine it with I and you get a d-bar operator, and because the curvature is the symplectic form, it has no 2-0 part. Sorry, 0-2 part.
For any sigma.
For any sigma. Because omega is always 1-1, and that's because it's invariant under I. So they all become integrable structures. Every time I choose a Kähler structure, I get a holomorphic line bundle structure on that. Okay. And so what I will be looking for is actually connections in this bundle in such a way that parallel transport along curves in T will give me identifications of the Hilbert spaces. That's the aim of this game here. To try to understand how do we build these connections. And then we'll use parallel transport to try to identify the different Hilbert spaces for the theory. But of course, if this connection is not flat, this isomorphism will depend on the path. Okay. So a few elementary observations. So if I'm for some reason given a Hilbert space structure, so a Hermitian structure in this bundle over T in the quantizations, well then of course, the parallel transport will be unitary if and only if the connection is Hermitian. Okay. Well, first thing to note. Second of all, as I sort of just said a little bit about, this parallel transport is projectively independent of the path if and only if the connection is projectively flat, which means that it is a 2-form on T tensor the identity. Okay? And third, if I have an automorphism group of the line bundle, which gives me an automorphism, symplectomorphisms on the base, and if T is gamma equivariant, this setup here will give me representations of groups closely associated to gamma if the connection is projectively flat. And further, these representations are unitary if and only if the connection preserves Hermitian structure. So I'm just saying elementary things to just set our minds about where are we in this. Okay, so now let's look at how can we possibly construct such connections. So now I just look at this family of complex structures. So I just view it as a map from T into this vector space. So when I do this, I can take a vector field V on T. So it's important you remember that V is a vector field on T. And I can differentiate the complex structure with respect to that vector field. And now what happens is that if I differentiate, so it's of course again an element of the vector space for each point in the parameter space. And if I differentiate the equation I squares to minus the identity, what will happen is I discover that this will anti-commute with I, with the elementary, just to differentiate this equation. And so therefore, actually, it always breaks into two pieces, which are these two off-diagonal pieces with respect to the decomposition of the tangent bundle into the holomorphic one and the anti-holomorphic one. And I call those two pieces with a prime and a double prime after.
So what is a VI?
It's the derivative of I with respect to V. So I start figuring out what is the variation of the complex structure and the very sort of explicit tensor ones. Okay. So now I want to make the definition that a family of complex structure is holomorphic if and only if T is also a complex manifold, and if I take a vector field on T and I split it into its holomorphic and anti-holomorphic part, and I differentiate I get exactly the same splitting as we saw here. Then it's a holomorphic family. This is actually equivalent to if you take M cross T and you use this family to endow the total space with a complex structure, then this will be an integrable family. I mean, it will be a complex manifold fibering over T. Okay. So this little sort of computation here is important to remember for the rest of the talk and understand. Okay, very good. So now what I will be looking for is I will sort of consider the trivial bundle, which is the one made up from smooth sections. And then that bundle of course has the trivial connection because it's a trivial bundle. And then I'll be looking for connections of the form, the trivial connection plus a one form on T with values in endomorphisms of this big bundle.
So now is it bundle over what?
Over T.
Over T.
All the bundles over T. And of course I would like to do it in such a, how do you normally get endomorphisms of smooth sections? Well, that's by differential operators, right? So I'll be looking for one forms on T with values in differential operators acting as sections of L to the K. Okay. And of course I don't want any because I'm really interested in the subbundle, right? So I want to choose U in such a way that it preserves the subbundle I'm interested in, namely the subbundle consisting of holomorphic sections. Okay, so then here is a very little elementary lemma that says that the connection we just discussed, if you're given some U, like this, so you're given some one form on T with values in differential operators, this guy preserves the holomorphic subbundle, the subbundle of holomorphic sections, if and only if U satisfies this equation here. So it is extremely elementary to prove this lemma. You just take the condition for being holomorphic and you differentiate with respect to the vector field and you will end up with this equation here for U. So in other words, every time we can solve this equation here, we have a connection in this bundle. All right. So now there's something we can remark about this equation, and that is that if I look at a vector field which is an anti-holomorphic vector field on T, then that guy has the wrong type to be contracted with this tensor here. So therefore that contraction will give you 0. And so actually in that direction, so in the anti-holomorphic directions, you can just choose U to be the trivial 0. And that will give you a connection in the 0-1 part. That is simply just saying there is a natural structure of a holomorphic vector bundle of this thing, of these spaces of quantizations in this case. So we don't have any problems with the connection in that direction. It is in the 1, 0 direction on T we have problems. Okay. So now I want to discuss something that is sort of an important technical tool in this field, and that is to introduce the fact that it locally preserves holomorphicity. And this makes sense if this guy is given by differential operators. And so it is exactly the same equation as you saw before, but now you only do it for an open subset in M. So you just, instead of doing things globally over M, you just zoom in on a little open subset and you require, so if it's given by differential operators, of course it also acts locally because I can restrict differential operators, and so just require this on all open subsets. So it should preserve holomorphicity locally on M also. That's what I call preserve holomorphicity locally. All right. Then there is this very interesting little lemma that says that suppose we have two connections of this form, and suppose that they are given by one forms on T with values in second order differential operators. So they only go to second order. And if we know that the simples are the same, I'm sorry. The lemma says something else. The lemma says that if you have two connections which locally preserve holomorphicity, and they're given by second order operators, then the second order simples of the two operators must agree. So this actually gives quite a hard, aim at proving unicity of such connections that are given by second order operators. And second order operators are, of course, prevalent in physics and so on, right? But, okay, so, a corollary of this is that if it preserves, holomorphicity locally, then the space of such use is an affine space based on, one forms with values in this set here. So this is holomorphic vector fields, and this is holomorphic functions. So for example, the typical thing would be, when you're on a compact manifold, so there's only constant holomorphic functions, and let's just say that you don't have any infinitesimal symmetries of the Kähler structure, so you have no holomorphic vector fields, then it's unique. That tells you that this connection is unique if you restrict to second order operators. Okay. Now let's talk about the Hermitian structure. So here are the other Hermitian structures I would like to consider in this talk here. So it is very similar to the L2 inner product that I had before, except now I just weigh it with a function like this, and this. So I should. Yeah, I know all the notation, but you don't. So HK is a function from T, which takes values in smooth functions on M. So I can evaluate such a function in sigma. That becomes a function on M. I can exponentiate it, multiply it onto this volume form, and then integrate inner products of two sections. This is a new Hermitian structure in this bundle, and now the inner product all of a sudden depends explicitly on sigma. And so this gives me a Hermitian structure in this bundle here. And so one way to try to get connections would be to say, let me take the Chern connection. So there's a unique Chern connection in such a case, right? So its 0-1 part should be the bar operator, and second of all, it should preserve this Hermitian structure. But if I take this guy, then I have questions like, what's the curvature of this? Is there a way I can choose this function such that it's projectively flat? And can I get an expression for u, in this case here, in something I can manage and work with when I want to quantize functions? Because I haven't discussed quantization of functions yet. Okay. So let me show you that if you were hoping that we could always do it in such a way that we get a projectively flat connection, let me kill that illusion for you by taking, something very concrete. So I'm going to take two complex manifolds, N and T, in such a way that N fibers over T. So think of N as this family of Kähler manifolds fibering over T. Now I'm going to take a line bundle on the total space of N, and I'm going to assume that all the higher cohomology groups of the restriction of L to the K along the fibers of this projection is 0. So
that's
if,
essentially the setup that we've been in all along.
more or less, but not explicitly. There could, for some crazy reason, be a, right? Yeah. Okay. So, but this will guarantee that I have a sub-bundle, okay? Because these are the obstructions for this thing to jump in dimensions. And now I take T pi to be the leafwise tension space to this projection. And then the Grothendieck-Riemann-Roch theorem tells me that the Chern character of this bundle, down on T, the push forward, right, is take the Chern character of L to the K in the total space, take the top class of the leafwise tension bundle, and push that forward in cohomology. So this is a formula for the Chern character. So let's look at that. So, you know, we have several of the things that go into this formula very easy. The Chern character of the line bundle is totally computable just by the first Chern class of the line bundle. That we know it's omega. We can decompose formally the top class of the leafwise tangent bundle like this. And then the Grothendieck-Riemann-Roch formula simply gives us that the Chern character of this pushed forward thing is just given by this linear combination. And now, let's assume that the push-forward bundle admits a projectively flat connection, which is unitary, because then I can use Chern-Weil theory to say that, well, in that case, the Chern character of the push-forward has to be the rank of the bundle times x of a two-dimensional class, namely the class of the symplectic, you know, this omega, capital omega that I showed for many slides ago. This gives you these relations here would have to always be satisfied. But let me give you an example where these relations are violated. So let's take the universal curve over the moduli space of curves. So CG over MG. That's a beautiful holomorphic family of Riemann surfaces. And the pre-quantum line bundle is actually the cotangent bundle, fiber-wise. I can take the kth powers of those. Indeed, if k is bigger than or equal to 2, I will have these conditions are satisfied. There is no H1. So therefore, I can now compute the push forward of this guy here. And this has been done already. It's very, very known, and it's expressed in terms of the kappa classes. So now I can take this expression, the kappa classes on the moduli space. I can ask, do they satisfy these relations? And it is super easy to check that they don't. Because the first few kappa classes, depending on how big the genus is, are algebraically independent. So they don't satisfy these relations. So this bundle does not support a projectively flat connection. Period. So we don't expect this in general, of course. Okay. All right. So in the rest of the talk, what I want to try to do, and so this isn't quite true. I don't want to do this all today, but so let me skip this slide. Okay, because I will skip the moduli space applications and just consider the general setting. Okay. So. But let me now follow Hitchin's work here, because Hitchin was really the first to somehow really do this in a non-flat situation. So, you know, the Kähler manifold can have curvature, right? And so if we're really looking at flat space, then this is well understood, and it's classical theory that has to do with the metaphlectic representation. And Hitchin was the first to do this in a setting, namely the moduli spaces of flat connections on the surface, and that guy has, you know, this family of Kähler structures that it gets from Teichmüller space. They are all curved. They don't have zero curvature. Okay, and so what Nigel was saying is, okay, I take this tensor here. So this is a tensor on this, you know, it's a section of the dual of the tangent bundle tensor the anti. Holomorphic bundle, right? It's half of the derivative of the endomorphism. I can turn this into a symmetric 2 tensor by just defining the symmetric 2 tensor in such a way that when I contract with omega, I get this derivative here. Because omega is invertible, this can always be done. So I can define a symmetric 2 tensor this way. And then what he said is the following. Let's assume that this symmetric 2 tensor is holomorphic. So this is a huge constraint on what kind of families you can look for. So I call this rigid families of complex structures, because you can't really deform the family much if it has to satisfy this.
I'm confused about the notation.
Okay.
The T sigma is the tangent. I'm confusing the T with the...
Yeah, so this T is the parameter space, and this is the tangent bundle to T. Yeah, no, I appreciate it. But so this here lives just over M, and it's a symmetric tensor of the tangent bundle, second order, and it's created through omega from the deformation of the complex structure. Okay. And so Nigel was saying the following: if we have A, B, C, then we have a projectively flat connection. Actually, he wasn't. He was saying in the cases where we are considering moduli spaces of flat connections on a surface and T is type-polar space, he could prove all of this. And so my contribution is to isolate out what are the minimal conditions he used. And the minimal condition is G is holomorphic, extremely important. And then second of all, this phenotype condition, namely that the first Chern class of the symplectic manifold is proportional to omega, the class of omega. And second of all, H01 of M sigma is 0 for all sigma in the parameter space. If you have those three conditions and M is compact, because M has not been compact until now, but if M is compact, then you get this conclusion. You get a projectively flat connection which is given to you by second order differential equations. Or operators. And we can be extremely explicit about which guy it is. So here it is. So U is a one form on T. So I have to stick in a vector field in U. Then I get an operator. What is this operator? Well, here it is. So there is a second order part, a first order part, and then these two combine to be a 0 order. What are the constituents? Well, first of all, you need the Ricci potential. So because we have this phenotype condition, we know that there exists a map from T into smooth functions on M with the property that, the difference between the Ricci 1-1 form and lambda times omega is dd bar exact, and that gives you f up to a scale. That's the Ricci potential. So that's what goes in the F's here. Now what is G? G was this quadratic tensor we had from before, right? Symmetric second order tensor. So how can I build a second order operator out of that has symbol G? Very simple. I take the 1-0 part of the connection in the line bundle, I land here. Then I use G to go over to the tangent bundle, tensor L. Now I use the Levi-Civita connection, 1-0 part, and the 1-0 part in the line bundle to arrive at here. And then I contract the tangents against the cotangent vectors, and I arrive back at this space. That's the second order operator. So this is an explicit construction of the second order operator that Nigel built. And I want to stress for the rest, just because that is an interesting point, the way that Nigel built this connection was to say, I start with the derivative of the complex structure. I built the quadratic tensor G. Then I built the second order part of the operator. And I start checking whether it satisfies the equation it needs to preserve holomorphicity. It doesn't. But then he understood that if I add this first order part to it, it almost satisfies the preservation. In fact, if I then add some extra term, which he didn't give an explicit formula for, but I gave this explicit formula for it in terms of the Ricci potential, then this guy here satisfies the equation. Point is, you built the operator from the top, second order, first order, 0 order. Okay?
This is just the standard heat kernel construction.
This is just the standard heat kernel construction, if you like. But done on...
But also this is just projectively flat. It doesn't say anything about unitarity.
That's right. Unitarity has to be verified independently by some means. But the projective flatness, Nigel used this integrable system that we all know about, right, on his Higgs bundle moduli space. And in fact, what we have done is produce a proof that doesn't use this. It turns out that if you just take this differential operator here and you compute the curvature brute force and be a little bit smart about it, you can actually prove this is projectively flat. So it's nothing to do with the Higgs bundle situation.
I think I got confused. So you mentioned this h, this exponential h, when you perturb the L problem.
Yeah.
So when this h? Is that
We
this?
will return to this. It is not present right now. So, and this is also what Tony was remarking. Nigel built this connection, but after he built this connection, it's sort of perfect for Chern-Simons theory when we're looking at moduli spaces and so on, except that it doesn't answer unitarity. Is it actually a unitary connection? So I have proved later by very indirect means, yes, it is a unitary connection. But that's maybe for, I mean, I'll do that next week. I'll show you how those arguments go. Because I want to somehow look at the general story today. Okay. I just want to remark that actually you can drop that M is compact in this game here if somebody hands you the Ricci potential. So the only place that compactness is used here, in my way of proving this theorem, is by using this condition to build the Ricci potential, to show there is a solution to this equation. If somebody comes and says, here's the Ricci potential for you for this family, then you can just build the connection. You don't need this cohomological condition, you don't need M is compact. Not for the projective flatness either. Okay. So this is what I state here. Okay. And I just remind you that the projective flatness, I then need to add this condition here, because if M is not compact, this is not automatic, of course. And also I still need this condition for it to be projectively flat. But it's projectively flat and it's projectively unique. So it's a very nice guy, right? But only unique up to considering second order operators. Okay. So here's the story I will do in Sunny Beach.
No, I have a question.
Yeah.
So suppose the original family is algebraic.
Yes.
Is the resulting, two questions. First of all, is the resulting connection algebraic? And second of all, can you give an algebraic formula for the resulting?
Yeah, this is the way Nigel did it. So I've done everything purely differential geometrically. He did it algebraic.
Yeah, this kernel, it's exactly like potato functions.
Okay. And so now here comes the thing that deviates significantly from what Nigel did. And so I want to focus in on this condition here. So remember I had A, B, C. And what happens is that B and C can actually be eliminated if you consider metaplectic correction. And that is applicable to moduli spaces or parabolic bundles and so on, and I skip that part completely now. But I consider this less of a contribution. Okay, this is the real point is to remove the holomorphicity of G. Okay. So let's discuss this now. Well, let's, you could have maybe have this condition here. I mean, if you had that, you see that there's no option for G. You can't deform the complex structure at all and still stay within that picture, right? And so an example of that would be, if you look at this universal curve, it has this property. So Nigel's construction does not apply to the universal curve over the moduli space of curves. Too bad. A very nice algebraic situation, right? Okay. Because if this is zero, that is zero, you can't deform the complex structure at all. So we need to somehow remove this condition. So let me try to show you how I do this. So I want to introduce a specific map. So I have a family of complex structures, so that they're all Kähler structures, with respect to the same symplectic form as before. And now I define a map from L tensors on M to L minus 1 tensors on M, tensor T bar star. And it simply goes the following way. You take your tensor, and then you contract some multiple of omega plus some other multiple of the Ricci 1-1 form. So just this specific combination here. K is the power, and L is the order of this tensor. So this is a K-dependent map. So omega, rho is the Ricci, and yeah. And now there is a very explicit, nice, recursive way to define Lth order operators acting on sections of L to the K by this recursive formula here. So you want to stick in a tensor of size L. Well, we know how to stick in tensors of size 1. And by recursion, we know how to do it for 1 less. And then we take the derivative, because we want it to be tensorial in the tensor. So if I just took this is not tensorial in the tensor, of course, but if I do this correction term, it is tensorial. So this is a way to construct operators of order L whose symbol is GL. Very explicit. Okay. So now I want to introduce a somewhat funny gadget, namely a divergence type of thing. And this divergence is, you take if L is equal to 1 and 2, you just apply the Libby-Civita connection to this tensor and contract. And you only apply it in the 1, 0 direction, of course, because the other thing would contract to 0. And then for L higher than or equal to 3, you do this one here. So this recursive construction here. And then a very long and cumbersome computation shows you that if you take the operator I just introduced of order L plus the operator of order L minus 1 of the divergence of this tensor, and you apply the d bar operator to that, you get exactly this. So here you see d bar applied to G, and here you see my algebraic action, psi L of G. So this is a very fundamental lemma. It's a long computation to do it. But that's important. So why is this important? So this is joined with one of my former students, Rasmus. So why is this important? Well, it's important for the following reason. Suppose for some reason you are given a set of tensors like this. They depend on K, and they are L-order tensors, in such a way that when I apply my algebraic map, this construction of omega and the Ricci form, I get d bar operator applied to G, one less index. So I'm assuming I have a solution to this recursive system. And not only that, I also assume that the first guy is a function f. So what I'm aiming for is a quantization of functions. Okay, so I have a function f, and now I want to find a system of tensors which satisfies recursively these equations here. But it starts at 0 order with f. My claim is the following, that if I have such a system here, and I define the operator f hat to be this infinite sum here, then this here, and so of course this here has trivial divergence. This is not very hard to check. So then, if this operator here is well defined, because now it's an infinite order differential operator, if this thing is well defined, it will map holomorphic sections to holomorphic sections. And so here, well defined means, for example, that this here is convergent, say, some Sobolev norm. Okay? So if it's convergent in a Sobolev norm, it's a triviality to check that this gives that this preserves holomorphicity. You take a holomorphic section, you multiply it by this operator here, and now you apply the 1 part of the operator. So you just stick in the definition. Move it inside the sum because it's convergent in Sobolev norm, so you can do that. And then you just use the lemma we had before, so we get this. This here is exactly why I wanted these to be 0. So the equation is just this is 0, so therefore this is 0. So this is actually an operator. Well, if it takes holomorphic sections to holomorphic sections, it's actually a quantization of functions.
Sorry, so which data do you use actually for this quantization? What data actually are you using?
So I start with a smooth function.
Yes.
And then I say, if you can solve this system here.
Yeah, so there is this family, and this depends on this family.
Yeah. So that's right. So this quantization has as parameters solutions to these equations.
Yes, okay.
And if you have such a system, I will get to existence and so on, of course. But right now I'm just presenting it as an abstract thing, right? You start with a function, and if you can find a recursive system that satisfies this, and that this sum here is convergent in some Sobolev norm, so that I can move the d bar operator inside the sum, then boom, that is an operator that takes holomorphic sections to holomorphic sections.
So does this operator depend on, it depends on the sigma?
Yeah, first of all, it depends on sigma, it depends on k.
Yes, okay.
The power of L.
Yeah,
and it depends on sigma. It's very important it depends on sigma, because notice I take something that is independent of sigma to begin with, because I take an observable, and that's a classical observable. That doesn't know about polarizations at all. Yeah. It's the temperature in this room, for example. That function I want to quantize. But the thing is that what this is leading me to is the quantization depends on sigma. That's very important.
And again, what is T sigma?
What is what?
T sigma.
T sigma. This is the holomorphic tangent space, but I don't see any T sigma here. What? Oh, there, sorry. Yeah, this is the holomorphic tangent point on that guy, on MC. Okay. So, of course, what I can do abstractly is I can define an algebra, subalgebra, I don't even know, maybe it's just a subvector space of functions for which this actually gives me a well-defined operator. Because if it is a well-defined operator, it will map holomorphic sections to holomorphic sections.
So you don't know if it is well-defined or...
Oh yeah. Okay, that'll come. But I just want to say that what can we actually say in this case here in terms of Dirac's conditions? So what I can say is actually, if you look at analytic functions on M, so if M is real analytic, and if you look at real analytic functions, this series is convergent. Okay, and it gives you the following Dirac conditions. If you multiply the operators, it will be the operator associated to the product of the functions up to a 1 over k. And if you take the commutator and multiply by k, this will be the operator associated to the Poisson bracket of two functions plus 1 over k. So it's a kind of, it solves the Dirac equations to first order. And that's completely well known somehow in this game here that we can't satisfy Dirac equations, but we would like to have this. So this is indicating it's doing exactly the thing we want from physics. Okay, so now, yeah, so what I can say is the following in general. So, this here, that this works, was a little bit of a cheat. So what actually happens, okay, is that if you look at a function which is real analytic on M, then the series for F will actually be factorially divergent. So this series here will be factorially divergent. So it will not be convergent. And so normally, or sort of many of us just say if something is divergent, we throw it away, right? But in physics, this is a very, very wrong thing to do. So how do we deal with divergent series? Well, there is a technology that allows us to deal with this, and that's called, Borel resummation. And so I think in the interest of how much time do I have left?
15 minutes.
15 minutes, okay. So I really want to get to the end of the talk. So, and it could take me a long time to expose for you what is this Borel-Laplace resummation of divergent series, but a completely standard thing. But, so real quickly, if you have a divergent series, you would like to produce a holomorphic function in some domain in the complex plane in such a way that it has this divergent series as asymptotic expansion. So just to talk about it completely all over, because then you will kind of understand what is going on. So one way to do this, if you know that your series is factorially divergent, so that's the same as saying Chevret 1, is to do the following. You consider the Borel transform, and the Borel transform is very simple because it just multiplies by alpha factorial on the alpha minus 1's power of z. So you just formally just do that to the series, and if you do that, okay, then what you can do is you can consider the Laplace transform, and the Laplace transform is a formal inverse to the Borel transform. So in principle, you will get back to where you were if you do this first do Borel transform and then do Laplace transform. And now the point is that many series that are factorially divergent have very nice analytic expressions when you Borel transform. And so you can actually really apply the Laplace transform and get something out that has meaning. Okay. And so that's what sort of this resurgence business that we are doing in this Renew Quantum program is all about. So that's sort of what I'm saying here, that there are conditions under which you can actually see that this gives you a very nice function that's analytic, and you can understand how its analytic extension is, and there's this whole Acad theory of resurgence and alien calculus and so on. It's a huge package, but it's really nice. And so that's what I do here. I actually apply the Borel transform to the series. Now the series, of course, no longer preserves holomorphicity after I've done this, because this will screw up the recursion I have because of these factors. But then I apply the Laplace transform to this object. So I need to understand how this extends analytically. So that's where a big chunk of the work lies. Get this analytic extension and show you can apply the Laplace transform, and there is the operator. And so this is also a good sign for physics, because for physics you expect something like this to occur, that you get an auxiliary parameter this thing depends on. Okay. So that's the story of that. But I just want to So this gives you a means to construct operators for functions that preserves holomorphicity. Okay?
What is this parameter that you said?
Yeah, the parameter has to do with, you know, this extra parameter from the Borel plane. So if you like, formally you can put s equals to 1 and then it goes away. But it is a regularization parameter, if you like. So it's a way to introduce a regularization parameter.
Is it compatible with WKB?
Yes. So, but now what about connections? What about connections? So here we built operators for functions, but the whole part was to preserve holomorphicity. Can we do something similar for connections? And the thing is, if you compare these two slides, it's almost the same slide as for functions. There is one difference, namely here. At L equals to 2, you don't write 0 here, but you just write the derivative of the complex structure. And if you now do that, and you are now looking for a one form on T with values and functions that satisfy this recursive system here, then you can start, you know, with any A you like, and then you can start building solutions to these equations. And by the way, well, I'll get to that point in a second. So you do this exactly the same here, and now the point is, if you now make this series here, then this series here satisfies this equation here. It's a solution to this equation. So before we had functions, this term was not there. Now this term is there, just by this little change in the second order. And so this gives us a whole slew of constructions of Hitchin connections. And they are infinite order. And so what is going on here? Because what's going on here is that we can start with arbitrary 0 and 1 functions that takes values in smooth functions. Well, as long as these series can be controlled, so as long as they are only factorially divergent, I can build this whole slew of connections from this. And so what I want to, let me see what I have next. Yeah. So I just want to remark the following. Look at this equation. No, it's better. Let's see. I don't know. Maybe it's better to just go on. Sorry. So what I can prove is the following. That if you have that this one form is almost closed. So it's closed modulo 1 over k, then this connection will be asymptotically flat in k. So that's what you expect for very large k, you expect it to be asymptotically flat. If this here is only not quite closed, but of this form here, then it will be asymptotically projectively flat. But not flat, or not projectively flat, but only asymptotically in k. And so that's really what you expect in general. You cannot, as I showed you with examples, right, we don't expect to have flat connections always. This is not right. So, how does this compare with the Hitchin case? And here you will see now I treat the Hitchin case turned upside down. So I need to solve the system, right? So I start with the following one form on T. It's simply take the 1-0 part of the vector field and differentiate the Ricci potential. That is my one form on T with values and functions on M. Now I start solving the equation step by step, boom, 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 and I'm using that I have this Ricci potential, and what happens is that you start solving the equation system, but look at this. Here is d bar of the of the second order term. That's 0. So the whole thing truncates at 0 order. And so you really just get Hitchin's construction in this case here, this Fano case, where you have this very special condition that this is holomorphic. And so you see, that gives us a good idea. How do we solve these equations here? Do we actually start some way up in some high order, say second order, and then try to guess what the second order should be, then try to solve first for first order and for 0 order? Well, if we do that, the kind of equations you will have to solve is d-bar operator equations. This is hard, right? Solving PDEs on manifolds is hard. But if I go the other way, this is algebraic. And it has k times omega plus more stuff. Omega is invertible, so when k is large enough, I can always solve these equations if I do them in the other order. If I start with 0 order, then build first order, second order, and so on. I can always solve them. No problem with solving these in that case. So I'm not solving PDEs, but I'm solving algebraic equations. That's much easier. And so it was just a coincidence that Nigel could start at second order. The real story that's very general starts at 0 order and builds up, and it just doesn't truncate at second order. It's very special if it truncates at second order. The general story will go on and give you infinite series. So I just wanted to make this remark. I found this very amusing because I tried to follow Nigel many years of starting with the leading order symbol, and it turned out that's not what you should do in general. You should start with the 0 order. Let me just come back to the unitary thing. So I want to consider this Hermitian structure here. And so, I don't know how much time do I have left now?
5 minutes.
5. Okay. So, as I said before, I want to consider unitary structures that are of this form here. And now I would like to know, can I build this churn connection if I start with this unitary structure here? Because there's a unique churn connection with respect to this Hermitian structure. And the answer is, yes, within this framework, I know exactly what the churn connection is. It's namely given by these A's here completely explicitly derived from the Hermitian structure. And then there is, what I'm not writing up here is there are a certain set of differential operators that you have to apply to this function here. And then you just build the A's this way. So I understand how the churn connection is built from this unitary structure. And conversely, if you now give me the A's, and then I just iteratively solve this, and I prove that there is a unitary structure. Okay. Of course, formally in the beginning, because this will give you a series in 1 over k for this, and you have to show that that's convergent in every situation. Okay, so what I want to do now is sort of propose a new way of looking at quantization. So I will start the usual way that everybody else does. I will start with a symplectic manifold. And the typical thing you should think of is a curved phase space, where momenta is also curved, they are not linear. I have some subgroup that I would like to quantize with respect to, some symmetries I want to preserve in the problem. And then I also have some algebra of observables that I need to quantize. This is very real in the physical situations. They say we need the following function, the following Hamiltonian to be quantized. Then we start with pre-quantization, so no change to that. Then the quantization really in a significant way will depend on which family of complex structures you've got to choose on this. So you choose a family of complex structures, and if you have a symmetry group, you make sure that this choice is preserved by the symmetry group that you want to quantize. Then you look at this bundle here. I'm assuming it's a bundle, right? Gamma will act on that bundle. And now what I do is I pick, say, suppose I go this way. There are several possibilities, but I go this way. Now, I choose this Hermitian structure. So I decide what the Hermitian structure should be. So I give myself some expansion like this of a function in such a way that the unitary structure is given like this. And then what will happen is that there will be a unique Hitchin connection, which is preserving this unitary structure from that. And there will be a formal operator like this, in such a way that when you compose that formal operator with my quantization operator, then what happens is that you get a quantization which commutes with the connection. Meaning, you have some sigma here, you build the operators here, then you have the parallel transport over here, you build the operators here, and this is all compatible. This is, of course, what you want for quantization of functions. You want that the way you identify the polarizations is well behaved with respect to the way you quantize functions. Now, this is something we've never obtained in Chern-Simons theory before this. So, for example, we don't know how to quantize holonomy functions, but this is a scheme for doing it. So, I want to make the following one that I really think, the quantization depends highly on T. And another way I can say this, if you want me to paraphrase it in physics, is the following. If you take, say, a photonic quantum system, so a squeezed laser light that is sitting in some squeezing cavity, if you have a gravitational wave that hits this quantum system should undergo a unitary evolution, and therefore it should be possible in principle to measure the gravitational wave passing the quantum mechanical system simply by the fact that it changes the Kähler structure as it goes through. So it curves the space. And so this is only possible if you believe what I'm saying, namely that it depends on the Kähler structure, the quantization. Okay, so what you can say is that the bigger the symmetry group you want, the smaller the family you can afford. So if you say, I want a quantization that has symmetry group, the symplectomorphism of the manifold, I think this will force you to only be able to quantize constant functions. I can't quite prove this, but I think that's right. So there's a trade-off between how big a symmetry group you want to consider. And then the bigger space of observables you want, the smaller t also has to be. So those two go against each other. You cannot quantize all functions consistent with varying polarizations. Simply not possible. There was also no-go theorems to tell you this is not possible. And if you take t to be a single Kähler structure, then actually you can quantize all functions that are analytic by the means that I described. So all functions are quantizable as long as you don't tamper with the polarization. Yeah, and so I already said the last part. So, yeah, so thank you.
Thank you very much. Are there more questions?
If you go back to the previous, your first, say the quantization really depends on the choice of the, you mean that in some cases you don't have this projectively flat bundle, and that is fine?
That is perfect.
Well, that is a revolution in quantum mechanics, right? Because we all learn in quantum mechanics that the rates, the projective space is what is relevant. So
yeah, but it's because they consider flat space. So my claim is that you should be able to see when the space curves. This should, you know, you start with flat space, then you start curving space, and you come back to flat space. This is a little contractible loop in the space of complex structures, right? So if you had a projectively flat connection in that case, this would be a trivial endomorphism of the quantum system. I am claiming that the parallel transport of these connections are not trivial, and that unitary evolution you would see should be measurable. And I just translate that into words in physics, saying if a gravitational wave hits a quantum mechanical system, it should undergo a unitary evolution you possibly couldn't measure.
So this is, how is this linking with quantum gravity? I mean, sort of,
I don't know, because this is treating gravity classical and quantum system quantum. This is not quantizing gravity.
Yeah, but you see gravity somehow.
You see gravity. Yeah. And the funny thing is that if you look at these equations here, so I mean these equations here, with this thing here, if you compose with I and make it equal to 0, this is Einstein's field equation for vacuum. So this tensor here is kind of, in some sense, measuring how much are we changing the curvature of space. And the curvature of space therefore enters in how you quantize.
Any more questions?
I have a stupid question. So you build this system of equation recursively, and then you get in the end something which doesn't converge. So cannot you change the system such that you get something converging instead of?
No.
No.
And the reason is that if you change the system, you won't preserve holomorphicity.
Yeah, so this is necessary.
They're all completely uniquely determined, step by step, because omega is invertible.
Okay.
So they're kind of, I mean, they're uniquely given. You can't tamper with them.
I have a question. So you quantize this with this hat sigma.
Yeah.
What happens if you take the traces of this hat sigma and try to expand on K?
Yes.
Is it a geometric
Yeah, I mean, you will see exactly what you expect. So to leading order, it's the average of the function over the manifold. Let's say it's a compact manifold, it's at least easier to. Then you see the average. You will see a 1 over K expansion of the spectrum. And in particular, the trace will be, to first order, the volume, I mean, the average of the function over the manifold. And then there will be correction terms. The next one will be the average of the Laplace operator with respect to sigma applied to F. There's some twisted in some way. It's not exactly this. But there is some big asymptotic expansion of the trace in terms of powers of 1 over K.
One technical question. The technical question is, usually you see this kind of infinite order differential operator whenever trying to invert some pseudo differential operator.
Right.
I think maybe you didn't write it explicitly, but you have all these long series. Do they condense somewhat if you just write which pseudo differential operator you're inverting?
I don't think so, really. I mean, you know, it's possible you could come up with a nice kernel formula for this, okay? But I haven't found it yet.
And then the last technical question is, during this discussion, you made some claims about uniqueness, which seem at some tension with the claims that it depends on T at the end.
Well, that was for families where you have this rigidity.
So otherwise, there's no.
No. So there, but if you want it to be coupled to a unitary structure, there is uniqueness. So if you fix the unitary structure, there is uniqueness. But you can vary those. I mean, you either vary the connection and demand let the inner product be determined, or conversely, you let the inner product decide what it wants to be, and then the connection is determined.
And what is the point of allowing this inner product to vary?
Well, the point is that, for example, the right one for Chern-Simons theory does that. I mean, I really don't believe that the other one is physically the right one. It should depend on exactly the physical situation you're looking at.
Meaning physical or physics?
Physics.
No, why do you say one is right and one is wrong? What's the criteria?
No, I'm not saying any of them are right or wrong. I'm just saying there is a correspondence between connections and unitary
You
structures.
said for Chern-Simons, one is right and one is wrong.
Oh yeah, that's because we have a path integral formula which we can do the asymptotic analysis to and figure out that the right one is not. So what we already know in Chern-Simons theory is that the right inner product is the L2 inner product, but where you weight the volume form by e to the minus a half times the Ricci function, the Ricci potential. So that's because we already know that Hitchin's connection is the right one in that case, because by the work of Axelrod, Della Pietra, and Witten, they derive from physics means that that's the right connection for Chern-Simons theory.
I see. You write that formula to get.
And then you can check, does Nigel's connection, does it actually preserve the canonical inner product, which would be the L2? The answer is no. Then you can say, does it preserve e to the minus a half times the Ricci potential? No, but it does so to 1 over k in order. And then you can actually find a whole perturbation expansion. The next one is, a Laplace operator applied to the Ricci potential, and so on. So there's a 1 over k expansion in that case as well. So the unitarity is very complicated, and it's been a mystery for a long time. But I'm actually, by other means, implicitly, we knew that the connection was unitary by my work with Kenji Ueno, where we sort of first show that the Hitchin connection is the same as the one that comes from conformal field theory, and then the one coming from conformal field theory, we know already is unitary.
So the case you have had in mind all the time is the Hitching situation of flat connections.
That has motivated a lot.
Static unit space.
Yeah.
You will tell us by the beach, I guess.
Yeah.
But are there some examples in higher dimensions, meaning not on a surface, but some modular space on a complex surface, K3 or something, where you get a projectively flat connection?
Yes, there are. So if you look at moduli spaces of flat connections on Kähler manifolds, then Peter Scheinost considered this, and I think actually very generally he proved that the family of complex structures you get on the moduli spaces in that case satisfies this G being holomorphic, and therefore he extended Hitchin's approach to that situation. But they all satisfy this G holomorphic, so it's very trivial in relation to this. Right.
And the connection is projected flat.
And the connection is projected flat. So, it's a very general thing. The moment that G is holomorphic, this is what I was showing you in the beginning, this theorem. So as soon as G is holomorphic, flatness follows, provided you have these few extra conditions. Provided you have these, no holomorphic functions. That's clear if it's compact, right? And then you shouldn't have any infinitesimal holomorphic deformations. So no holomorphic vector fields. Then it's unique and projectively flat as a second order operator acting on the space.
This
This infinite order differential operator that you construct inductively,
Yeah.
does it have a direct relation, in the theta function, non-abelian theta functions case, does it have a direct relation with this infinite order correction you have in the Oldster? Or, when you fix the unitary structure and you want to adjust the connection by doing an affine shift by going to higher and higher order in the Theophilus quantization. You have this argument that says you get actually a unitary connection which is flat in that particular case. Is it the same type of reductive construction or is it different?
I would say yes and no, because when you say theta functions and so on, you are implicitly telling me that you're considering flat space. Rn, R2n with the family of complex structures which are linear.
Non-abelian theta.
Non-abelian theta functions. Then you are telling me, look at the moduli space with semi-stable bundles and so on. But the thing is, G is holomorphic.
Yeah, G is holomorphic.
So we don't deviate from this. So the connection is given by a second order operator. But the functions, you are absolutely right that in that case, the quantization of functions can be done via Toeplitz operators, if you like. And then you get a similar phenomenon occurring with a 1 over k expansion. But I'm not exactly sure how these two tie together.
I don't know if they're correlated.
Yeah, surely they must be somehow, but I don't know exactly how this goes. That's right. And so there I had to implicitly, so if you do the following, the functions in the Chern-Simons theory, they're given by holonomy functions. So you have a closed curve on the surface, you compute the holonomy of the flat connection around that, you take the trace, that is a function on the moduli space of flat connections. It's of course not holomorphic, because we're talking about real connections. You can multiply that onto holomorphic sections of L to the k, and then you can project back. And that Toeplitz operator is the leading order guy of the true curve operator that you get by pushing this off into surface cross I and thinking of it as a knot in there and quantizing it via Chern-Simons theory. But this gives you all the perturbation theory, order by order, of this guy. And so that's some progress. And we didn't know exactly that this was given by an infinite series of differential operators and that they're given exactly by this recursive system. So that's what it does in this case.
So maybe we have many questions, but maybe last 10 minutes. So thank you very much.
Thank you.
So maybe we start so let us start the second talk of this afternoon. It's by Professor Bestislav Apostolov from University of Quebec at Montreal, and his title is Weighted Constant Scalar Curvature, Parametrics and Applications.
Thank you very much for the introduction. And of course, it's always a big pleasure to be back in Bulgaria, in Sofia, and this time a big honor as well to be invited to this very successful, interesting conference. So I will talk about a problem in Cantor geometry. This by now is sort of a classic subject, and I intend to start the talk with some quick review of this problem in Cantor geometry, and at the end of the talk I will tell you some ideas that I have been involved in recently. So this Calabi problem is motivated by even more classical theorem, which is the uniformization theorem due to Poincaré and Kiob. And this theorem tells you that on a compact Riemann surface, you can always find a Riemannian metric of constant Gauss curvature, and let's say volume 1. And if you normalize the volume to be 1, then this metric is unique up to complex homomorphisms. So this is kind of a really important classical result, and it has many applications to tight linear theory, for instance, and so forth. And what is interesting is that back then Poincaré imaging a proof that is very important for us and for Cantor geometry. So what Poincaré argued is that you can start with a some arbitrary Riemannian metric and try to deform it by multiplying by a positive smooth function to take the one you want, one of the constants Gauss curvature. And if you write what you need for this new metric, you will find partial differential equation for a non-smooth function on your Riemann surface. It's the famous Liouville type equation. So here K is the Gauss curvature of the background metric, and C is the constant of this constant curvature you want. And by Gauss-Bonnet, you realize that this constant actually is a topological data that you know in advance. So what you really want to solve this PD for the non-function f. And today we know many proofs of the existence. So this kind of old result is the motivating point for what Calabi proposed to do in the setting of complex manifolds of higher dimension. Okay, so the idea is to go from Riemann surface to high dimensional manifolds. So the object of interest is Keller metric. So Keller metrics have been introduced by Keller in the 1930s. And this is sort of a Riemannian metric compatible with a complex structure. And as most of you, of course, know, it's given by, so it can be defined in the following way. So this is kind of a global object. It's a Riemannian metric on them, but around each point you can find a holomorphic coordinate chart such that your metric is given by the real part of a Hermitian matrix given by the complex Laplacian of a real valued function. So this real valued function is called local potential. So you want the real part to be your Riemannian metric. It's given by one function. And of course, if you take the imaginary part of this Hermitian symmetric matrix, you will obtain a form instead of a Riemannian tensor. This is the so-called Keller form, and can be written in local holomorphic coordinates like this here. And more invariantly, the Riemannian metric and the Keller form are linked through the complex structure as we saw in the previous notes. And as you see by the fact that you have this formula, the Keller form is closed, and therefore it defines the rank class on the manifold. So now, kind of direct computation allows us to compute the scalar curvature of this Riemannian metric using this potential function. If you do the computation carefully, you get an expression. So S omega for me will the scalar curvature of the Riemannian metric associated with the Keller form. And it will be a fourth order PD, very nonlinear. So this Ij is the Hermitian matrix corresponding to the complex Laplacian of a real valued function. So you take log determinant of this, you take some sort of a complex Laplacian. So it's a kind of what's important is that it's a PD which is expressed in terms of one real valued function. So we want this to be constant. That will be the problem. And now I will consider the case when M is a compact complex manifold, Keller manifold. It would have at least one Keller metric, omega 0, which is the background metric. And what Calabi asked and worked on for extended period of time, he asked whether we can find a new Keller metric which has constant scalar curvature and for which the Durand class of the Keller form is fixed. So, as before, one can see that this is kind of a PD problem. So the first observation is that this constant here is topological again, as in the case of uniformization theorem. Actually, if I integrate this constant, take the mean, it will be expressed by intersection numbers homology. So this would not depend on anything, so it's a priori constant. So effectively, what Calabi is asking is to find a new Keller structure, omega, for which the scalar curvature is given by that constant. And from what we said before, this would be a PD, and to make it global, so that's where this assumption of homology class comes from, you could actually see that the difference of these local potentials defining omega 0 defines a global function, which I call calligraphic phi here. So now this will be a global function of the manifold, and the formula for scalar curvature will be a PD for this unknown global function. So that's the Calabi problem. Okay, so this was kind of an influential question because it has been worked on for quite some time. So the first definitive results were obtained by Urban and Yao. They consider a special case of this Calabi problem. It's a case where the Acad class is minus the first-order class, or if you prefer, alpha is the first-order class of the canonical bundle. And in that case, the problem has been solved. They prove that you can always find such a metric. And Yao as well solved the case when the first-order class of your manifold is 0, so then the claim is true for any Acad class on such a manifold, and what you get is the famous Calabi-Yao metric, which also are Ricci flat. And in both these cases, the important thing is that this fourth-order PD can be actually simplified to a second-order PD because of these assumptions here. But people realized short after this works that in general, even in when C1 this is positive, in our case, this problem is obstructed. There are examples where you cannot find solutions. So it took some time to understand these abstractions properly, so that we'll kind of review what we know today. But the first thing I will do, I will kind of tell you from the point of view of the PD what we know about this problem. So to understand what happens from the point of view of PD, it turns out that you have to consider a variational problem associated with this question. And the right variational problem was introduced by Mabuchi in the 80s, who introduced a functional he called K functional. That's a really important letter from my talk, as you'll see. So this is a functional on this space of Kellen metrics in a given Kellen class. We saw that they are parameterized by these functions, modulo constants. I can always add it on to this potential. So it's really the Kellen metrics will be essentially this space modulo constants. And Mabuchi observed that he can introduce a functional. I kind of quote how he did it, although today we get a slightly probably better idea. But what he said is the following. So essentially, he wanted a functional whose critical points are precisely the solutions I want. So he defined the differential of this functional that he wanted to define. So it will be given by the scalar curvature, but so it's your PD times phi dot, so critical points by default are our solutions. And he observed that actually this was rather a one form on that space. But he observed that this one form is closed and this is contractible space, so it has a primitive. So introduce this functional like this. And then there was already in the Urban world there were some sort of tools, one of which I now recall is the so-called J functional of Urban. This is another functional in the space of Karen metrics. I will define it in terms of this function phi. It doesn't matter, this is kind of complicated, but it's an explicit definition. What is important to see that all these terms here that I integrate there, they have sign. So this functional J will play a role of a norm. So this K omega is not a linear space per se, but you have this kind of norm on that function, this norm on that space. And here is the main statement on the PD side. So we'll make this theorem A. So what it says, so I will fix a maximal torus, compact maximal torus in the automorphism group of M. I will also assume that this torus is in the reduced part. I don't want to be technical here, but roughly speaking, you take the automorphisms which project trivially to the organized torus. It's a closed subgroup in the group of automorphism in general. And so one can fix this torus because Calabi showed that if you have a solution, it must be invariant under a maximal compact subgroup. So I will always have a solution that's T invariant. So we can work T equivariantly in all this setting. And the main analytical result tells you that you can solve the PD if and only if this Mabuchi functional K is coercive in an equivariant sense. So we want that K is bounded by, so you have some kind of a uniform constant, positive constant, so that you can bound your functional by your norm. So this simply means that you, so let me see, represent this. So now this is, let's say this is this space K and omega, and you have this, so it's an open, you know, to be Keller is a kind of an open infinite dimensional condition on the space of functions. So you have this J, which is kind of a norm, the J functional. And what this condition tells you is essentially that this Mabuchi functional should be somehow bounded by this J function. Okay. So it turns out that this K energy is convex, and if you have this right behavior, asymptotic behavior, then you will have a critical point, and that will be your solution. That's kind of a, you know, of course it's an infinite dimensional picture, but that's the picture you have there.
So is this automorphism? What is AUR? Is it automorphism?
Yes, sorry, that's a typo.
What does R mean?
R means that reduced part. So you take the projection to a Belize torus, and you want this to be zero. In other words, this is the subgroup of automorphisms, for which you know, the Lie algebra is holomorphic vector fields. They have to have zeros. Or if you prefer, any T-invariant geometric T-will-act coming from it. This is a complex. This is a complex invariant turns out in this character. Okay, so it's kind of a well-defined. So here is the so this is kind of the black box that synthesized the results on the PD side. Of course, in this subject, there's a long history. I will try to throw some names, but I would apologize if I'm not precise. Much more names I could put in this. But in the direction that if you have a solution, then you must be proper. It goes back to Tian, actually, it was conjectured by Tian. He proved this properness when there are no automorphisms and in the Fano case. And also Tian considered some inequality, something lambda J to some positive power, so it's not linear like that. But the linear growth was established by Fones, Armstrong, Vankov in 2008. And this is the case where you don't have any automorphisms. So it was a very important result, technical result of Berman and Bernson in 2017. They proved that actually this Mabuchi functional is convex in a suitable weak sense. And they also proved that then by convexity that actually it's the critical points are necessarily minima and they unique up to the action of these complexified terms, which explains why I consider this kind of a equivariant version. And this result that I stated in the direction here was really established more recently in combining works of Darvas-Rubinstein and Berman-Darvas-Liu. And the other direction is the harder direction, where if you have properness to prove existence of the PD. So in the Fano case, when there are no automorphisms, this goes back to a paper, Lezioni's paper, and Dink and Tian. It's back then it was kind of a link to the Tian alpha invariant and continuity methods. But there are kind of a more recent approaches, purely variation to this statement, which are to Berman, but they seem to get very big. This is for the Fano case, with no automorphisms, and there was a very recent breakthrough due to Chen and Cheng, 2021, which proved the theorem A in full generality. So that's the kind of analytical part. So what I will do next, so we know now existence is equivalent to this properness or coercivity condition on the function. But we want to have a criteria, we want to decide whether this function is proper or not. And this is this idea of algebraic resolution of the problem that I will review quickly. And it's the main object is what people call now equivariant test configuration. Just to explain what I'm doing, very roughly speaking. So you have all these potentials here. I will define some kind of a subset of potentials, array of potentials, which are associated to this algebraic construction, which we call test configuration. And the idea is to decide on this picture just knowing what happens on these test configurations. And of course, then there will be questions about density. That's the main idea. So what is a test configuration? So the test configuration is one way to define it is so in previous talks a little bit of that, but so I start with a Keller manifold with the data fixed as before, and then the test configuration will be another Keller manifold of one complex dimension Bohr, and it will be endowed with a T action as well as my starting manifold, an additional C star action which commutes with this T action. So I will augment the dimension of the torus as well. And this C star action plays a special role, so I denote it by rho. And what you want essentially is to have a surjective morphism from your test configuration for your manifold of dimension 1 more to the projective space P1. So on P1 I will consider it as C star plus 0 plus infinity. So I have a C star action on P1. And I want that this special C star action, this extra C star action, is equivariant. It kind of preserves the action on the base. Then what you want as well is that this, so I will take a point on the base, P1, and the preimage will be, in general, will become some kind of variety, but I want this to be kind of actually a smooth variety, will be a copy of M. And I want it to be equivariantly isomorphic to my manifold here. And each time that I'm away from the central fiber. So what the idea is that you have your P1 with 0 here, and you will see copies of your manifolds. You will have some central fiber. And this C star action will move copies of your manifold, and it will degenerate them to something perhaps singular, which corresponds to 0. So this is M0 here. So this is Mx for x. And so this fact that I'm over P1 and not just on C is encoded in the fact that I would like at infinity to see again as something trivial, as I see, away from the 0 fiber. So kind of a complicated as a definition, but let's just give some examples. The basic trivial example is to take a product. So you have a T action in M. You have a C star action in P1, so this will be the two gadgets. So we have a T times C star action. Now, this satisfies everything, and moreover, the central fiber will be again a copy of your M. And here you have a whole family of Keller classes that you could put, so that you get so you can put Keller class on alpha, and you can put any positive multiple of C1 on the O1 of P1, so you get a kind of a family of test configuration in the sense that the Keller class here. And so this, essentially, in this theory, that's the only example you really need to know. Because then I will start deforming this example to obtain some kind of more interesting test configurations. And what I can do, just take the product, take a subvariety of M, which is kind of invariant under the T action, so I want to be equivariant. And what I will do, I will blow up this subvariety times the 0, the origin in P1, and I will get a total space which satisfies my conditions. You'll have a blowdown map, and then projection on P1. This will be the projection P, and it will be equivariant by some kind of obvious reasons. And it turns out that you can also adjust the Keller class in here. It's kind of a Sichardy type condition that was done by Ross and Thomas, I believe, in that setting. But it will be a whole interval of parameters and Keller classes such that this will define a test configuration. So essentially, you blow up a product, and more generally, you can do modification of products. You can blow up, blow downs, morphic information. So that's essentially what you need to worry about. So there is another kind of a natural procedure that you can do. You start with some test configuration. You already have it, for instance, the product. And then you have this T action now. So now this is very, very specific for the equivariant setting. So we have already T acting on your test configuration. And what you will do, you will take a S1 corresponding to some element in the algebra of the torus, and this will give a C star action corresponding to that choice. And now you can twist the given C star action rho by this other C star. So you get a new C star action. So there is a slight problem with this. You will not have triviality at infinity, because this twisting will be seen on infinity, but you can equivalently glue a product. So you can kind of untwist at infinity only. So that's what's called twisting, or twist test configuration. In particular, the twist of the trivial are called product test configurations. Okay. So these are examples of test configurations. Why we care about test configurations, how this is linked to our PD? Well, that's kind of a really idea going back to Dinketian in '92. So what we'll do, we will fix a Keller metric on the total space of the test configuration. It's just a Keller metric, and we will make sure that it's invariant under the all symmetries I have. Okay. So then, what I will do, I will use the rho, the C star action that I privilege, to create a one parameter family of Keller metrics on the total space. And what I will do then, so I have this omega t, which is rho e minus t plus e s star omega, and I will fix a particular fiber. For instance, this corresponding to x1, so this will be n1, which is isomorphic to n alpha. And I will restrict this one parameter of family, Keller forms on the total space, to this particular fiber. And what I will get a one parameter family of Keller metrics on my metric. So this is called rays, smooth rays. So I will have so this rays will correspond to what I wrote here. So this red points. So I will, given a test configuration, I have a ray. I have many rays because I can vary this omega, and I can also vary the test configuration. So this will be the particular test functions, if you want, that I will use to see this picture. So this is a definition of a ray. And the idea of Dinketian was to ask how we can relate, how we can actually check the coercivity of K from its behavior on these rays. And they actually observe some interesting things. I will come back to that in a moment. So now, to understand how we will do this effectively, so in more modern language, it's just kind of a wording here of nothing scary really, but it's called non-Archimedean functional. So the idea is the following. I have some functional. In my application, this will be the K functional. I have some functional on the space of Keller potentials, and we say that it's a non-Archimedean version if for any for any test configuration, the equivalent test configuration as before, and any invariant form on the total space, this slope, this derivative affinity of the functional is defined, and so it's the same number, and this number only depends on the data of your test configuration and the rank class. It's kind of you should think of some sort of topological event, essentially. Okay, so this is just a property, not putting anything. Now, we have this coercivity condition here. So what we want is to take rays. So I will take omega t here in that thing, And I will divide by t, and asymptotically I will see that if I knew that I had a non-Archimedean versions, I would get a kind of an inequality here between the non-Archimedean versions. The first observation, it's kind of a recent point of view actually, it's very efficient actually, is due to Buxton, Simotu, Johnson, and extended, so this is in the polarized case, the projected case, this has been extended by Sjostrom, Dierfeld, and Dervan in the Keller's equation that I consider. But essentially this G functional, the band functional, admits a non-Archimedean version. I'm not writing the precise formula, it's kind of a little bit complicated, but it admits, and actually it will have a sign with 0 if and only if you are in the product case, product test configuration case. And even more recently, Hisamoto proved that this, so remember here I have this infimum over the orbit of the complexified torus. And so I will call this infimum the function of JTC. So what Hashimoto proved actually using this result, the previous result, in the polarized case, he proved that actually you can have a non-Archimedean version of that thing as well. And it's given by some infimum of the Buxton-Hisamoto-Johnson version when you do the twists. So what you do, you start with your test configuration, you can associate to it its non-Archimedean version of the test configuration, and then you start twisting with this, as we define. Twist of test configuration, and you take the infimum. And essentially, it's reductive groups, it's achieved and everything. So it makes sense, and this provides a non-Archimedean version of all this stuff here. Okay. Now, because of that, we have immediately a corollary. So that's what we would refer to T-equivalent F stability, some abstract function of F. So if we have an abstract function of F, and if this abstract function of F admits a non-Archimedean version, because we already did this for J, then this coercivity, equivalent coercivity, will imply an equality like that. So the non-Archimedean version of ML, the test configuration will be bigger retail than lambda, this some sort of norm with equality if and only if you are in a product test configuration, so a twist of a tree. So it's kind of a general principle, you see, so it's the Brown's property. And of course, in the classic case, constant scalar curvature, people by now know how to compute the non-Archimedean version of K. So this is the second main theorem in the theory, that this Mabuchi function will admits non-Archimedean version. So I now specify you have to consider test configurations which are T-equivalent as before, perhaps smooth for this talk, let everything be smooth, but in general you can take normal. You want the central fiber to be reduced, no multiplicities. And then it turns out that the non-Archimedean version of K is given by an intersection number. So essentially topological thing, as I promised. And in the case when the test configuration is smooth, it will be important for what follows. You can re-express this intersection number as a differential geometric quantity. It will be integral over total space of your test configuration, the scalar curvature of this kind of Keller metric from the total space minus the topological constant of M, and some sort of this kind of volume form a priori constant volume. And as a corollary, of course, of this theorem, we get that if you have a constant scalar curvature Keller metric, then your T-equivalent K stable in the sense that you will have these inequalities of the non-Archimedean version of the consumption. So this has long history as well. As I said, the basic idea goes back to Dink and Tian. They assume no automorphisms, Fano, and they assume that the central fiber is an orbifold. So they express this non-Archimedean version initially as a differential geometric invariant on the central fiber. By the way, this intersection formula, this is kind of a equivariant homology intersection, so you can localize on the central fiber. C star action will fix the central fiber. So anyway, but the first evidence was given here with some simplifying assumptions, and Donaldson he also defined this essentially this non-Archimedean inversion in terms of the central fiber, which could be a very degenerating. So he really did an important input in this. Later on, Paul and Tian kind of had already idea of this kind of global expressions. They considered, well, not test configurations, but in the projective case, they embedded a manifold in a bigger projective space, considered C-star subgroups, and express the same thing as intersections on that projective space. And there are also works of Fonskin, Ross, and probably the most important input was by Wang and Odaka, who found this kind of very nice intersection theory on the compactified test configuration that I just presented. So I would say that, in general, if I don't assume that the central fiber is reduced, it was much more recently known that actually there exists a non-Archimedean version. It will not be given by this intersection formula I gave you, but it's in the good side. So it will. So the real thing will be strictly less than the intersection. So it's still enough to test on the intersection. And the theory also works for more general Keller test configurations instead of projective. So in this previous works, the projective case, in the Keller case. So that's what's known, and that's not what's not still known. So the conjecture here, the main conjecture of that subject is that we can decide case this cursive if and only if you have these inequalities on all test configurations. So we need this to happen for all test configuration when again this DF was the intersection that I referred to earlier. And that's precisely corresponds to what I said here. So essentially, if we know the symptotic behavior of these two objects on test configurations, then we can reconstruct.
Excuse me, I forgot what was this TC coercive.
Yes, this is the equivariant version because you see what happens is that if you have one solution and you acted by complex automorphisms, you get another solution. So you don't expect in general to have unicity. And this TC, so what you do, you fix a maximum torus once for all in the automorphism group of your manifold. Let's say in the projective case, that's what you do. You fix a maximal torus, and then you complexify. So this is a compact, and this is just C star. Okay, and it suffices to consider only tori, only abelian version. So that's another point of this theory that has been realized gradually. So and I modeled this action. That's what we have here. Okay, so that's the conjecture. And again, historical remarks. One direction is already done by what I said generally. If existence implies this case stability, abstract case stability principle applies. And then the other open direction, there are first of all works by Donaldson and Xu and Chu in the tori case. It has been confirmed in the tori case using some convex geometry. And indirect proofs go back to the breakthrough by Chen, Donaldson, Sun, another proof by Tian of the conjecture in the Fano case. There are many other proofs these days. Perhaps I will notice this latest results like Berman, Buxom, Johnson, Chile, and Zhang. What they prove really is directly proving from case stability coercivity, whereas the other proofs they use continuity methods to build a Keller-Einstein matrix, and then so nowadays we know how to do this directly.
And this property of coercivity is related to the geodesic stability, right? To the symmetric space. This K that you have there is an infinite dimensional symmetric space.
You're right. So that's something kind of embedded in the whole thing. But what I said is that you have to test on all these smooth rays, which also depend on the choice of a Keller form on the total space. What happens is that there is a unique geodesic ray, which is not smooth, unfortunately. It's C11. And these geodesic rays, so essentially it's enough to check on these geodesic rays. And indeed, that's where the function is convex really. That's
You're
where
appealing to the symmetric space.
yes, the formal symmetric space. Yes. But the point is also that there is a kind of recent series of results by Chile, which kind of they use really the non-Archimedean geometry in an essential way. But it looks like that we're very close to some sort of inverse. Anyway, so that's the survey part of my talk. Now, what I want to tell you today. Well, what about if I don't have this subtraction is present? So what about if I'm not stable? Okay, stable. And you don't have to look too much for an example. For instance, if you blow up P2 in one point, you get the first Hirzebruch surface. It's a final manifold. So I will take the Kelly class, which corresponds to the friction class. So this, the automorphism group is not reductive, so we know that it doesn't admit any constant scalar curvature even by Tsushima theorem. But people look at this example and then constructed various interesting metrics. I know of at least 3 very interesting Keller metrics. So the first interesting Keller metric was constructed by Calabi back in the late 80s. So what Calabi proposed to do is to look, instead of constant scalar curvature, to look for metrics in this Keller class for which, if you take the gradient of the scalar curvature with respect to the metric, you get a holomorphic metric. Of course, if the scalar curvature was constant, this is trivial holomorphic metric field. In general, that's what he proposed. So this is kind of a viable subset of this thematic now to look for extremo instead of constant scalar curvature. Then there were another push in this. There were works of Koiso Sakama and Tian and Zhu. They consider the Ricci solitons, that's linked to the previous talk somehow. So the idea is that now you have this Ricci potential, so the Ricci tensor of your metric minus the metric will be an exact form. So you tell a Ricci potential. You want this Ricci potential to generate a holomorphic vector. It's kind of similar there. And there was another, 10 years later, let's say, so it's kind of an interval. The time interval is not here, but more recently, Mortelli Sparks and Yao considered the question of the existence of a Calabi-Yau cone matrix on the cone. So you take canonical bundle, you take the zero section, you contract it in a point, you get a fine cone on some Cn. And on that fine cone, you want to build a cone Calabi-Yau metric, Ricci flat Calabi-Yau metric, which is conical. So so these cone metrics are something that we also saw in previous talks. So this cone is non-compact manifold with singularity, but the type of metrics you want. So this is Cn. So what you want in here, you want a calorimetric, which you write as dV bar of a positive function, so kind of a Stein situation, and you want this to be Liouville, actually, with respect to a vector field. Z. So these are, and you want to be the Calabi and Ricci. So they consider that, and their work inspired a lot of interest. For instance, I'll probably return to that later, but there were works reworking the whole picture on the cone, which is very nice. So we had a small contribution to this, that we realized to build such a metric on the cone is the same thing as just this Ricci solitons, similar thing rather. So you need a calorimetric omega-3 such that the Ricci minus omega-3, again, you have a potential, but I will renormalize this potential. I will write it as coefficient n plus 2, where n is the dimension of the manifold, dt log h, or some positive h. And now I want again this h to be a holomorphic potential. And this turns out to be equivalent to have such Calabi-Yau. So you see 3 different, they are different, they're not isometric, so we have 3 different interesting metrics. And of course we want to have a theory that englobes all these species at once. Right? So this was essentially in the PhD thesis of a former PhD student of mine, Billy. He And it has a lot to, I suspect it has a lot to do with the previous talk, but anyway, so I'll tell you what we proved. So here is the setting. Again, you have your fixed torus as before. Now I will fix another data. So I'll consider a space of t-invariant Keller metrics in the Durand class. They are t-invariant. And the fact that I'm in this reduced part of the automorphism is equivalent to saying that such a t-invariant Keller metric, the t-action will be Hamiltonian with respect to measure. And when I start moving within the fixed Durand class, okay, for each representative I have a moment map, and it's known by classical results that this polytope can only move by translation. So I will fix once for all the polytope, which will normalize the momentum. Okay. So for instance, if you have a polarization, everything is canonical, but if you're in a Keller case, you have to fix this polytope. And the new data will be two arbitrary, well, almost arbitrary smooth functions. So one positive and one just any smooth function defined on the polytope. So this will kind of weights. And what Lagdili considered in his PhD thesis is he plugged these two functions in the PDE corresponding to the constant scalar curvature. How he did that, so it's a formula. Well, we will return to this formula in a moment, but essentially you pull back this function by the corresponding normalized momentum map, you get a smooth function on the harmonic node. This is the usual scalar curvature. Then you take the Laplacian of the pullback of this, and then you have some sort of, the Riemannian metric and the Hessian. They are bilinear forms on dual spaces. So we have sort of trace, natural trace with respect to the metric. And you want all this, what he calls V scalar curvature, be the pullback by the momentum map of W. That's the thing he wants to solve. Probably just to say very briefly, so this expression can be obtained in the following way, to make a link with the previous talk. Essentially what you do, you have a torus action. Each S1 generates kind of a linear operator in the projective case, a linear operator on the space of sections, of your polarization. And what you do, you take the eigenvalues of these operators corresponding to S1, and you apply to them V, and then you start considering the quantum limit, taking powers of your vector bundle. And what happens, you take a asymptotic expansion, Bergman type asymptotic conception, and then with this weighted thing, you find this weighted scalar curvature as a second term in the expansion. Anyway, I will probably not go into this, but that's the definition. And these three different remarkable Keller metrics on first Hirzebruch surface happens to all fall on this in this terminology. As you can see, the constant scalar curvature case corresponds to take V to 1. So when V is 1, you see the scalar curvature. So this is 0, this is 0, and W will be your logical constant. And then the Calabi extremal case corresponds when V is 1. And this W is an affine linear function, so when you pull back by the momentum map, you get a potential of the Killing vector field. And it turns out that these scalar-rich solitons, there are another weights to put into the equation, and so forth and so forth. And what kind of we were achieving more recently, we with this thing, we try to see as far as we can get into the theory. So one of the results that we proved with Lagdili and Joubert is that if you have a solution of this kind of a weighted PDE, there is a technical assumption on W weight, but all the examples were satisfied, then you have coercivity. And in his PhD thesis, Lagdili already observed that if you consider smooth test configuration with reduced central fiber, you can find a very similar non-Archimedean version of the weighted K energy. And as you see, it's kind of as previous, but just instead of the usual scalar curvature, you take this weighted scalar curvature and correct accordingly. It's a very nice generalization.
Is this weighted scalar curvature obtained also as a moment map condition?
Yeah. So what you do is, so as you know, this moment big picture, you have a formal symplectic form, and what you do, you take the trace of the variations twisted by the complex structure, and instead of integrating against the symplectic form, you integrate against this weight. So you pull back by the molecular, V positive weight, so you get a new symplectic form. And you need a L2 product, then W, plug W in this, and that's what you do. Yeah, absolutely. So as a corollary, we have these things. We have that existence implies some sort of a uniform weighted stability. And by the way, this is new even for external metrics, external calorimetrics. And so this really, this non-Archimedean version is that was not done. How much time I have?
I think 15 minutes.
Okay, so that's kind of one of the things. Now I probably will return to this case as before, the application to Sasaki geometry or to scalar flat Kerr cones. I want to elaborate a little bit. So here the idea is the following. So you see, I was talking about the canonical bundle for the Hirzebruch surface, but more generally, you can take any polarization. So I will take a polarized variety, and instead of canonical bundle, I will take the dual of the polarization. So the total space of the dual of L minus the zero section, which I will contract to a point. So this is again an affine cone. And I want to obtain, okay, so this T action that I had before, I will lift it to L once for all, so I will call it T hat. And this is the definition of a cone metric for some psi in the Lie algebra of T hat. And instead of reach equal to 0, I will rather consider scalar. Okay, so that's the problem we want to apply our formalism. It has been studied a lot by Sekilikidi, Collins and Sekilikidi. What they prove using the code directly, they prove that if you have a solution, then it's semi-stable, which means that you have just sign of this non-Archimedean thing. So you cannot say when it's 0, for instance. But let's see what our result gives in that situation. So this red vector field, it could be irregular. It could generate a whole torus. I don't assume that's a C-star action, but assuming a moment that it was a C-star action. So the idea is that this C-star action will correspond to some quantization, which corresponds to a function, and this function will be a fine linear function on the polytope because you have a homomorphic character. So this zeta hat will correspond to a positive affine linear function on the polytope that you associate with your projective variety. Uniquely, you don't have this object. So this will be the weight. This will be the function to build the weight. So our observation is that you have this condition here, if and only if your initial manifold admits essentially Vw constant scalar curvature with precisely these weights, where this L is the affine linear function corresponding to zeta. Now it's just off the shelf, right? So now by the previous result, we know that existence implies uniform case stability, and we kind of improve immediately this theory, theory in terms of affine cones developed before by Collins and Sekilikidi. I'll probably give you a kind of a very artificial, perhaps, idea of some of the problems and the ideas. It's very brief. So how different this is in the classical case? So what is the point? These weights, working with weights. So in general, I would say that there is now a fairly well-established principle how to check if a given function is coercive. That's due to Darvas Rubinstein, and it's completely abstract theory. Essentially, you need properties to check and to verify, and then you're done. And it uses somewhat kind of a subtle functional analysis. So essentially, what I would do now first, I would define a distance metric in the space, in this space K, in the space of Kerr potentials. How I will define this distance? I will take a path in this term matrix. Well, this is a calligraphic phi, sorry, this phi dot. So I will take the derivative of these potentials, absolute value, and I will integrate against the volume form of the corresponding caliber. So this is a length. You take the infimum of lengths between 2 points. Nothing guarantees this is a metric, so it's a deep theorem due to Shushan Chen. Actually, Shushan Chen showed something else. Yeah, anyway, Darvas was the one who noticed that the Chen result implies that this is a metric. And now I have a metric, and I will take the completion of this space of potentials with respect to that metric. So kind of abstract completion space. Okay. But the beautiful thing, due to Darvas again, is that this abstract space, you can realize it as a subspace of plurisochromotic functions of your manifold. It has a kind of a stronger topology than the topology here, the natural topology, weak topology of PSH. And roughly speaking, you're dealing with integrable, local integrable functions. So it's a very weak regulatory. Okay, so that's the idea. And now the properties you need to have for abstract functional to know that it's coercive are the following. So the first thing you have to worry about is how to extend your functional to this weak space. So you need to have a unique or natural largest lower semi-continuity extension. The second thing you have to worry is a convexity property. So this Chen result I quoted here. So what Darvas observed is that because of the Chen result, any 2 points in this space could be joined by geodesic with respect to this D1. So it's kind of a Finsler kind of situation. So you want to worry about the convexity of your functional along such geodesics. And then there is a uniqueness model in the orbit, model of this action of the minimizers. And finally, there is a compactness property of the functional. So now I will turn back to our situation, what we have and what we don't have. So we don't have anything for free, but some of the things can be adapted with some technical efforts. But from these 4 properties, let me say it's kind of very roughly that all but the first one were clear how to be done with persistence, introducing the weights and essentially following the ideas in the classical case. There is, however, the compactness. So we were very lucky that there is a kind of a very interesting paper by Berman with Nystrom and Hamidi. They're pursuing different problem, but essentially the compactness follow from their work. But the first step was problematic. And why it's problematic? So we define this K energy by its differential, but one can re-examine the definition and obtain kind of a more concrete realization. So we can write this K energy as an entropy term with a weight, plus something else that I don't care. And I remind you that the momentum map, the normalization of momentum map, means that you take the momentum map of your background metric, and each time you have omega phi, you just take the differential of phi increased by the complex structure. Essentially, that's how it varies. So it's a kind of you need some irregularity of phi to define this momentum. That's the problem. So you see, because of this weight, and because of that actually, here you need at least C1 regularity. So you cannot define this on the space of this PSH weak completed space a priori. So you have to worry. But what you can say is that if I had V equal to 1 and W something, I'm fine because I can use what other people did in the non-weighted case. They defined also this will be an entropy function now, and there are definition of entropies using Taylor-Bedford results and so forth. So roughly speaking, so the problem is V. W. And what's kind of surprising is that essentially the argument that allowed to overcome this difficulty is completely geometric. So I will present a differential geometric construction here. So the idea is the following. So I have my manifold M with a fixed data as before. And what I will do, I will consider principal T bundles over a base which is a product of constant scalar curvature polarized variety. So essentially, you take the product of this thing. So you need k factors, and k is the dimension of t. So each factor I can consider it as principal S1 bundle. Okay? So I take kind of a product of these principal S1 bundles, taking the product of the base, and I have a connection form on T on this total space, and then I kind of what I do, I glue a copy of M because I have a T action of M, and I have a principal T bundle, so I form a bundle construction here. And the whole point is that if I have a Keller metric on M, I can define a Keller metric on N of this total space. And this Keller metric will, it's fairly explicit, but it will be built from this constant scalar curvature Keller metrics on the base, and plus some kind of topological data. So here, these PJs are just, the bases corresponding to each S1. Okay, so I use the momentum map of omega m, and some constants which are topological constants. Okay, and this is the connection. So I build a kind of I wrap up a Keller metric on n, and the whole thing is to compute the scalar curvature of n. If you compute the scalar curvature of n, what you find is the weighted scalar curvature of n, but with a weight corresponding to this topological data of your principal bundle. These are polynomials. But what I will do, I will vary this data now. I will take bigger and bigger dimensions. So I have lots of polynomials. And you see, I can also write a formula for the K energy. So the K energy with weight 1 on the total space of n will be the K energy with weight P on n. And what I will do now, I have all these polynomial weights. For this, I know how to extend this guy, because that's what was done in the classic case. And now the idea is to use Stone-Weierstrass theorem to see that actually the extensions, which I know for these polynomial weights, will converge to something well defined, and will allow me to extend this weight functionals to any weights. So that's essentially the main observation which we needed to overcome this analytical process. So I will stop here. Thank you very much.
Thank you very much. Any questions?
So you said before this weighted constant scalar curvature also appears as moment map for the group of Hamiltonian homomorphisms. So you modify the symplectic form of the space form structures with the weights. Why is that natural, or where is this new symplectic form, the naturality coming from?
Well, if you think about it, it's kind of clear that it's another symplectic form. So, but our main motivation was to solve the simplifications, so which were so we start obtaining. Well, I told 3 generalization of constant scalar curvature methods, but there are many others. For instance, if you want to prescribe the scalar curvature of the toric variety, you also prescribe it. That's V equal to 1 and W. So there are also questions about constant scalar curvature on the total spaces of these models. And as we see, this is a P. So at some point we said, well, there is something going on there. So there should be some general theory. And we kind of afterwards discovered the GIT interpretation, which fits well.
Some other questions?
I was just wondering what one can say about the moduli space.
That's a very good question. So what we can say about the moduli space, that's really... Okay, so in the final case already, this case stability is producing a reasonably good moduli space. It's a lot of work to drag geometry. Now this case stability, which is equivalent to existence of Keller-Einstein metric, produces a moduli space around a smooth Keller-Einstein fan. Okay. Fujiki-Schumacher already observed that if you don't have automorphisms, and you consider existence of constant scalar curvature metric as your stability condition, then you have a locally Hausdorff space for the right. So when there are automorphisms, of course, there's a work to be done. But I think what I can say, I'm not an expert, but I think there is recent work by Dervan and Newman who essentially proved that this analytic stability existence of extremometric or constant scale curvature, even in the non-polarized case, can be interpreted as stability condition and define a nice local structure in model space. Now, how to quantify this? That's the really, and these test configurations serve for that matter too. So the idea is to how to, if you're not K-stable, how to degenerate to stable and to CP. So all the usual stuff is in there.
And can one hope for a type prototype theorem that, you know, if you frame that there is some kind of contractible space?
I think there is a Chi and Xiu proof something of the sort that the model space is algebraic, right? It's sort of it's algebraic Gorati minus divided is quite complicated. So even this is in the Pano case, okay? Pano case, but already we see a global structure. In the constant scale curvature case in general, as far as I know, there's no really any hope as yet of getting to this.
Any other questions? Okay, let's answer it again. So we take one speaker of this conference is Professor Andras Nemetki, who came from Alfred Rennie Institute of Mathematics, and if you talk on lattice cohomology of singularity.
Thank you very much, and I would like to thank the organizers for the invitation. It's really a great honor to speak at this conference. Actually, this is the title, and you already So this is the lattice cohomology of curve singularities. This is actually this is a part of a big project when so in a joint work with my student Ágoston Tamás, and this is a part of a project when we define different lattice cohomologies. Actually, many years ago, I defined lattice cohomology for the topological lattice cohomology for surface singularities. That is for links of surface singularities for a three manifold. And later, so very recently, we started to also actually since then we work on the analytic part, but now we succeeded to define for any isolated singularity in any dimension. So first it was the pair of the surface singularity. A little bit later I will say a little bit more about that. And also a higher dimension and also the Kerr case. The Kerr case is somehow a little bit special. Today I would like to discuss only about the Kerr case. So why is actually, so what is the goal that we want to define cohomology series? So what is the meaning of that? So if I have a reduced curve singularity, it's not necessarily plane curve. So reduced in any embedded dimension can be anything. And we define some object for any cube 0, 1, non-negative integer, like the usual cohomology. And but it has a lot of structure. Actually, it's a graded, it's a z-graded. So each Q is a z-graded and also has a U action. And somehow the grading is constructed in such a way that this is minus to the degree of U, like in the Hegel flow. So of course that all these constructions were influenced by the existence of some cohomology series in the topology, in the three-dimensional topology. And though the construction here is completely different, but somehow the structure of the cohomology is the same. It's a graded ZU module. And additionally here, if we have, of course, that in general we want to see what is happening with when we have the functors, so the morphisms of the cohomology. Here, if we have a deformation of reduced curves, then we have also functor. And that is a graded, for each Q, it's a Z-graded ZU module morphism. And the construction is analytic. Actually, it's from topological point of view. A little bit later, I will explain that if this is a plane curve singularity, then you have a rich topology also. And in that case, also the embedded topological type of the plane curve singularity it's enough to define, to recover this cohomology, but if C is not a plane curve singularity, then the topology is not so clear. So then indeed the construction is poorly, so it's analytic. So that is the analytic lattice cohomology. So maybe some more, yes, it's already, I said here something that if it's a plane curve singularity, then also from the embedded topological type, so that means that the link of C, the algebraic link also, that topological information, it's enough to recover the lattice cohomology. And also, a little bit later, we also will see this, that if we are in the Gorenstein situation, then we have even some additional structure, some Z2 symmetry. So like, so that the Gorenstein symmetry present in the algebraic geometry also will induce some duality, some symmetry also in the lattice cohomology. So, first, I would like to say a couple of words that how we define a lattice cohomology. It's already, probably in several conferences I spoke about this, but it's better if I recall the basic definitions, what I want. So at this moment we can disregard that I'm speaking about topological analytic or what dimension, just what is the situation and how we can define what do we need in order to define, say, a lattice cohomology. So somehow we need the lattice points. Here I wrote Z to the S or the positive quadrant. Here maybe I emphasize that it's not really essential, that it's not really the linear structure is important. I don't care about the linear. It's not really the linear structure of the lattice. What is important that I have some lattice points, say in R to the S. So that is exactly the natural, how they sit in the lattice points in R to the S, and somehow what are the neighbors? If I have a lattice point, then what are somehow the neighbor, what is a small neighbor or combinatorial neighborhood? That say lattice point and R plus EV, they are neighbors, that is a segment. So I want somehow this cubical structure, decomposition of R to the S. So that is what is important. Not really the linear structure of the lattice of the Z to the S. So I need some lattice points, say in R to the S. I need, using say a basis, I want to decompose, I have to see the cubical decomposition of the R to the S. And it's very natural how we do this. The 0 cubes are exactly the lattice points. The 1 cubes are the segments where I have a lattice point, and R plus EV when the immediate neighbor of in any direction I can go, yes? So I have the, say, if we have the, so that corresponds somehow my lattice, of course, that basically, no, it's not, okay, so maybe I do in this way. So I have the lattice points, yes, we have the lattice points, the 0 cubes are exactly the lattice points, the 1 cubes are of this type, so that is the 1, so these are the 1 cubes. And if I want a 2 cube, then I can go in 2 directions, that is the EV, R plus EV, R plus EU, and R plus EV, EU. And if I have one a three-dimensional cube, then I take I take 3 different directions, so subset of, and that is the, of course that this cubical decomposition gives absolutely nothing. So if I want a cohomology using this, I recover the cohomology of R to the S. So it's good for nothing in some sense. But what is important and what makes the difference is that I need a weight function. Yes, so that is basically, it's not basically the lattice point. The lattice points also is important that what is everything will depend on the choice of the basis. In many cases, that is very natural. In the resolution of singularities, those are exactly exceptional divisors. So that will be the somehow divisorial filtration associated with exception divisor. So that EV will be very naturally present in the situation. Also in the case of plane curves, will be the normalization and evaluation of the normalization. So again, will be very naturally present the cubical structure somewhere in some lattice. But what is important, the second main ingredient, and that is maybe the most important, is somehow the weight function. So for each lattice point, somehow I have I define an integer. Yes, and some finiteness property I also, that is not really essential, but let's assume that this is happening. Actually, in all the cases, what I consider this happening also in the case of surface case, that was somehow the weight function was negative, positive definite, and that is somehow the interior of some ellipsoids, and the lattice points in the interior of some real ellipsoids. So that is some finiteness we need. And then we define for each cube the weight of a cube, which is the maximum of the vertices. So it's very naive, so as you can say that this here is good for nothing, and even when I will define the lattice cohomology, you will say that that is just a stupid game. But at some point when we claim that, say, the Euler characteristic of this is the Seiberg within the surface case, that's already something. So is this cohomology will, the power of it is that indeed it gives something what is also in the literature and even new. So how we define the lattice cohomology for any integer, fix any integer, and then because of this actually it's the minimum of the weight functions, just starting from there I have to consider, otherwise this Sn is empty. So we consider these spaces. This is just in the usual topology of Rn, it's a union of some cubes such that the weight of the cube is less than n. What is the meaning of this? Say that just assume that this is some positive definite, yes, quadratic function, some real ellipsoids, say, defined over integers. But so if I have, say, that is the level set of w less than n on the lattice points, then I consider all those lattice points which have weight less than n. I consider that in Sn. If I have a segment and both ends have weight less than n, then I enter with that segment. If I have a segment that this is less than n and this is higher, then I don't put that segment. And also I continue in this way. So I consider all the two cubes. If all the vertices, yes, of the two cubes have weight less than n, I consider that two cubes. And in this way I continue with all the cubes. And of course that this definition actually tells me that if I have a cube inside, then also all the faces should be inside. Of course that here also I can define in a more general way that just for any cube I define somehow an abstract weight, but I should be careful that it's compatible with the definition of the faces. Of course that you can argue that, okay, why this probably it's all the time it's contractible. Well, it's not. For example, already here we can have a situation that here already the connected components. So I might have somehow that say this is the level set, this is less than n, this is less than n, and this is higher and higher. Of course that if I increase n, then this will be in the same connected component, but I create a new points. And not just the connected components, also H1 can be. Of course that I need then higher dimension. You can imagine that, say, I have a cube, and say that this has higher weight, this has higher weight, and somehow this is how I cut. And I will have here, maybe I do with a different color, then I will have here somehow a loop. So this will be inside, that is inside, that is inside, 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 inside. But I cannot put the two faces because that is outside, this is outside. So immediately I will have a, so it's very tricky. So this is somehow the weight function, how it's compatible with the position of the lattice points inside of RS. So it's, I'm not counting really the lattice points, no. Notice that how many lattice points I have inside of something. But it's the topology, how the really the special weight function what I will choose, how it's compatible with the situation of the lattice points. Yes, so that is what is somehow measured. So indeed, it's really in cases what I will consider, I might have here Sn which has non-trivial H1, non-trivial H2. So really the topology of Sn can be very, very tricky. On the other hand, you can imagine that sometimes it's not easy. I will write here some weight functions, and then it will be not really easy to compute, because say when I have rank 50 or even 10, say, to compute and see the neighboring, so that is the differential equation you want to solve, probably it's not so simple.
Sorry, can you just say, to orient ourselves, what is the input, the algebraic input for this lattice?
So,
is it just the lattice inside Rn and the weight function?
Yes, that's
or
it,
do we
and
also
plus
need
the weight
something?
function, plus the weight function.
That's it.
And this EV, the choice of the neighbors, say the EV,
So,
combinatorial neighbors. Yes, because if I take, you see, if I take another EV, say that by SL2Z, that base change, then if this is here, if I take, say, yes, if for example I replace this base by something this and this, then this immediately becomes neighbor of this, and this segment will appear. So it's really important that what is the choice of the neighbor. So I fix a lattice, I fix the basis EV and the weight function, and starting from there you have a lattice commute. So in some sense it has a lot of applications. It's very general. Many situations you can apply. Okay, so I have this Sn, and for each n I have a space Sn. Immediately we will see that that is actually a tower, because if I take a bigger n, then I will have a bigger Sn plus 1. And what is the definition of HQ? For any q non-negative, I define HQ as a direct sum of HQ Sn Z. That is just the usual cohomology, just the standard yes over Z. And so for any q, this is n graded, so n gives a grading, yes, and that is the Z grading. And also I have an action. What is the action? Exactly the inclusions of the corresponding Sns. So if I have, of course, that if I take bigger and bigger n, I have a bigger and bigger, so the inequality, so I have, if a lattice point has weight less than n, then of course it's less than n plus 1. You have the inclusions and the corresponding restriction, yes, that is the corresponding restriction, that is the U action. So that U action basically measures that how this tower fits how the inclusions.
What is the U action?
U action is exactly this restriction, cohomological restriction from Sn plus 1 to Sn. Sn, it's included in Sn, yeah. So,
Are you saying the U is uniform?
so let's take, yeah. So for example, here I have some lattice points, yes, and the very first, say, level set is somehow this. So say it's somehow the interior of ellipsoid, and the lattice point is interior of that one. Then, if this is say Sn, then I have these points and the two different connected components to H0. Then I put here 2 points. Yes. If I Sn plus 1, say, will be something like this. That say this is my Sn plus 1. Then what I will have, that I will have also this point, this point, this point, this point, but they are connected because note also the one segment is there, and this is somehow again independent. It's a different connected component. So in that is Sn. In Sn plus 1, I will have here this connected component and another point. And this point in Sn includes in this one, so that is exactly somehow the inclusions. And that is a new one. So that is the U action, and here the U goes to 0, and this goes to the side. So somehow that U action tells me that how long the cycle survives. If I make a bigger n and bigger n, yes, then at some point that is actually will be in all our cases that somehow if n is very big, then this will be contractible. If that ellipsoid say is so big, then indeed you cannot have these stupid surprises that you don't have enough room to connect the lattice points, and then will be contractible. But somehow in the beginning of the tower, you might have very interesting cycles. And the U action, how how survives those cycles and how they of course in H0 I can consider the reduced part, because you see in any SN I have at least one H0, so will be not, this is not a finite Z module. So you have somehow to separate, say, the tower, the Z tower of the H0. So we consider a reduced cohomology. So H0 is split. So starting from the very beginning, when the minimum of the weight appears, starting from there you will have a Z tower, and you cut out the reduced part of H0, and of course that for Q bigger than 1, bigger than equal to 1, then is the reduced is just the usual HQ. So we separate this tower. Actually, everybody who knows this Hegel-Fleur, and then that also there you have towers. Yes, the tau infinity, or yes, and also here we separate that tower. And in all our cases, what is happening that the reduced parts will be graded Z modules. So even over Z, the graded part, the cohomology will be finite Z module. So for example here, say, assume that after in the next step already everything is connected, then this will be, say, my picture that I have here Z, I have here Z, here I have a Z, Z, these are the U actions, and after that I have the infinite tower going up, Z, 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 Z. It's an infinite bamboo. Then if I cut this, that is the Z tower corresponding to the, say, fixing a point, and what remains, that is the reduced H0. And that is a finite Z module, and also for Q bigger than 0, the reduced part. Right now I just assume, but all in the cases what I will consider, or we consider actually will be finite Z modules. And then we have the Euler characteristics. Somehow this is from the reduced part, and this is the information from the tower, where the tower starts. So it's a little bit tricky, but actually you can do an exercise that, for example, if I have a finite, you can actually do this in the finite big rectangle, all this picture. And in that case, if we consider what Euler considered, that consider the alternating sum of the cubes, yes, then you have the Euler characteristic of the variety. Here you can do the alternating sum of the cubes with the weight, multiplied by the weight. Then actually a computation tells you that this is the right definition of homological Euler characteristic. Yes, so that is the right definition of the cohomological Euler characteristic of the cohomology. This from the tower, and this is from the reduced part, you have Euler characteristic. So that is the construction. So what we need, Z lattice, the neighbors, and everything looks very elementary, say the definition.
Excuse me, Andras. How do you count one cubes on the diagram at the right hand side? One cubes.
So in H0, when you define H0, that means that it's connected components of Sn. Yes. So in this case, in the first picture, I had two connected components. I had 2 points. In the second picture, what I had a point here, say, and it was, say, this one. But even if yes, again, 2 connected components, this and this. Okay, and after that, I just assumed here that everything is connected, and I have 1 and 1. In the H1 picture, you have to really see the cycles, and then I will show you an example. Really a plane curve singularity when the H1 is non-trivial. It's there, so it's.
One more question.
Yes.
In what sense this is a cohomology? In what sense this is a cohomology?
Well, it's a very good question. What do we expect from Actually, I have a ZU module. Yes, I have something associated with the curve. To the
what's the difference?
Sorry?
If this is a cohomology,
yes.
Does it have a differential?
No, that is already defined in just the cohomology, the output. Everything can be defined as a complex. That is a little bit longer, but it's an independent definition that you consider all the cubes here, and you consider all the ZU modules generated by all the cycles, all the cubes, and then you have an operator, delta operator, which now you have to consider the phases, but it's a little bit differently written. Yes, that if the usual one has plus minus, say some plus minus, yes, the phase, yes, that is the usual one. Of course, that is nothing here, but now I consider the ZU module generated by all these, and that the new one will be defined somehow in this way, that all the phases, and here U, and the weight of D minus the weight of the phase. Okay. And then you prove that delta composed with delta is 0. What is the cohomology? So you can define also in that way. Yeah, so it's, yeah. And also you have a functor, which is here what is, of course, that in general, we have that for any continuous map or good map, we have a functor where it's tricky. It's just for a deformation. For deformation, somehow we have a functor. And also some exact sequences in a surface case we prove. Yes, surgery exact sequence.
Can I make sure I understand? So you have some cell complex. You put filtration on it. You put some function on the 0 cells. Exactly. The smallest filtration compatible on the complex compatible with this function.
Yeah, you can take the smallest one, or even you can force a little bit with.
But in your case, you took smallest one.
Yes.
And then you get filtered complex, and this U is because filtered complex is the same as complex over CU.
Yeah, yeah. Yeah, that's everything. That's what kind of weight function I should choose in such a way that to get something nuts, something interesting. Yes, and this is just the cohomology has for H0 has an improvement that is called the graded root. That is exactly, I put the connected components instead of Z. Even I make points for the connected components, and if a connected component at level n, it's included in the connected component n+1, then I put an edge somehow. So I make a picture like this. That is the graded root. Some of these are the gradings of the, and root it's like the root of the plant, but it's a tree, basically it's a tree. Something like this allowed because two connected components might be in the next step in the same connected component. Something like this is not allowed, and so it has a very nice shape. In using this is much easier to write the structure. The U action, it's actually the edges.
So is there anything like this for the higher cohomologies?
No, it's no. Then you can make somehow simplicial complex that if I have here sorry, that here if there is something like that H1, then you can put so you can construct say a minimal CW complex where what it shows all this tower of essence. But most of the cases I'm interested on only so in many cases H0 is already interesting.
I didn't understand why one of these is allowed, one of them not.
So this is not allowed because what is the meaning of it? That one component at n level, yes, it's inside of two different components at n+1 level. Yeah, so it's the two components might join in the, yeah, and it can happen that something new appears, but all the time will be the shape of will be something like this, yeah, and then yeah, can be something like this. You see,
you're drawing the sub-level set.
Yeah. So it's real, and starting from here, it's not interesting, but what is happening here, it's really interesting. Can be very interesting. Yeah. Very good. Well, so that is already, yes, it's a graded root. These are the level Sn, the connected components of Sn. If n is very big, then it's empty. If n is big, then again, it's most of the cases will be contractible, and you have the structure of the root. And again, what I already explained, that if I have here, if I consider Z, and this, then I consider this tower. I separate what remains that is H0 reduced. And also, of course, that for H1 and H2, everything is reduced, and we have the Euler characteristic defined. I don't know if there's any question. So this is the general construction. So it's just, I need a weight function. And now I just historically, I want here to explain a little bit that what kind of, say, examples we have. The very first example was the topological lattice cohomology for normal surface singularity. In this case, it was, I consider, so it was a resolution, and EV were the exceptional curves. Yes, and I consider the free module generated by the exceptional curves. That is basically the second homology of X tilde. So that is exactly what we consider. Of course, that in that case, I have also negative definite intersection for that was used. And actually, that is a plumbing graph, yes, of the link, of the three manifold. So everything what we define in the combinatorial setup, say in the topological setup, is just the intersection matrix of this. So everything is in the plumbing, the resolution graph. Actually, I didn't wrote it that here I assume that the link is rational homologous sphere, so all the EVs are pi 1s, and also it's a 3. Well, in that case, I consider the Riemann-Roch expression for the W0. So L is an element of the lattice, yes, and that is just -1/2 L plus kx. That is a canonical cycle on the resolution, and that is the intersection form. Actually, that is negative definite. Because of this negative will be positive definite. So the real level sets are ellipsoids. But again, I want to see what is the compatibility between the Riemann-Roch function, yes, say, that quadratic function, and the lattice points, how they inside of the ellipsoids, how the lattice points are distributed, and for each level.
So
and
this assumes that it's a hypersurface singularity.
No. It just says no. Any normal surfacing of dimension 2, isolated. Say normal, not so. Not necessary. I don't use its hypersurface. Just I have a resolution. You have any case. You have a resolution.
Well, what was this about the link?
The link you can define in any case, because you just take the embed somewhere, maybe high dimension, cut with something. So the small neighborhood in some balls, or take some metric, and so yeah. So thank you. So it's the link can be defined. That is normal. That is real dimension 4. You take a small neighborhood. That will be the link. Will be oriented three manifold. Connected three manifold. It's a planned three manifold associated with any resolution graph, and maybe I emphasize also that Kx is here looks that is the canonical divisor of the X tilde, but by the junction formula, how the intersection with Kx is topological. That is the junction formula. So using the junction formula, this expression is completely combinatorial from the graph. So you introduce this combinatorial Riemann-Roch expression on the graph, and you get a topological, lattice cohomology of the normal surface singularity. It turns out, and the Euler characteristic in the sense of how I define, yes, it's the Seiberwitten invariant of the link. Here, if I take this one, then it's associated with the canonical species structure. If you want all of them, usually the Seiberwitten, it's associated, actually it's the normalized Seiberwitten, yes, but associates to any species structure an invariant, then we have to go to the universal abelian cohomology. I have to take here different characteristic elements. Here, if you take different characteristic elements, that means that I cohomologize in such a way that this is integer for any R. Then I have a huge family of lattice cohomologies. Some of them are not different, but you can list that what is the periodicity. Exactly the interesting one can be listed. They correspond to the species structure of of the link, and we will recover at the Euler characteristic level all the Zagreb invariants. Actually, it turns out that Zemke recently, actually, in many cases, I proved, and Ozsvát and Szabó proved that in some cases this coincides with the Hegar-Fleur, but no, Zemke verified in the general that this actually, this cohomology is the same as the Hegar-Fleur of the link. So it looks at how naively we started, yes? And even this Riemann-Roch, it's interesting, okay, but still you can say that Riemann-Roch of a curve, or non-reduced curve, yes? But still it gives an interesting theory. Well, this has an analytic version, and that was very interesting that I was hunting for that. What is that? Because all the time I was interested in these pairs, that the topological invariant and analytic invariant. Actually, this was defined in order, with my intuition, was that how I can compute the geometric genus, somehow topological bound of it. And somehow all this was invented because I wanted to understand the PG. Well, it turned out that also this has an analytic version if I define the weight function in this way. So that is actually associated with the divisors, I have the multivariable divisorial filtration. Yes, so these are exactly the functions, yes, whose, if I pull back to the resolution, the order of vanishing is bigger than L. Yes, that has a dimension, that is the Dilbert coefficients, and I consider that minus H1 of OL, where that is again the weight function, and I have a lattice cohomology. If we want here for any spin-C structure, then we have to go, the spin-C structures are, it's the torsor of our H1, when it's H1 finite group of the link, when it's rational homology sphere, we can go to the universal Billion cover, we have the H Galois action, and here I have to replace this by good, very well chosen line bundle associated with the corresponding spin-C structure. Again, we have a weight function, and we have the analytic lattice cohomology for any spin-C structure. Turns out that here, in this case, actually the Euler characteristic is the PG, the geometric genus, H1 of OX tilde. And if we consider any spin-C structure, then we have the equivariant geometric genus. And actually, this can be defined for any dimension, and then we have the Dilbert function, and this object, that is the pair, and then the difference is again a weight function, and then we have an analytic lattice cohomology.
So then you have H of n-1 or
n-1, if n is bigger than E, it's n-1.
And can you like motivate this?
Yeah, this is the pitch. So here the Euler characteristic, I forgot to write here, actually is Hn-1 of OX tilde.
Yeah.
So that is exactly the first in the mixed Hodge structure, the first block of the Hodge block. And that is actually there's a categorification of Hn-1 OX tilde, which is the geometric genus in a higher dimension, so the first block in Hodge.
But so, would it make sense to include, say, some other cohomology?
Well, I try, of course. It's we want to do everything, so all the Hodge, but right now what it's only it. And on the other hand, you see, this is really an interesting question. It's not about, that is a little bit not curved, but maybe it's interesting to say, this question, what I put it here, that how started everything? Started with, say, topological, in the surface singularity case, the topological, or the Hegar-Fleur, or I don't know. That was not motivation for me. At some point I realized that it fits with the Hegar-Fleur, but was a topological object. We found an analytic pair in the same dimension, but somehow that definition was so good that it was possible immediately to generalize. Of course, to show that this is a well-defined and this is the Euler characteristic is the right one, it's a lot of work. Also, you have to show that everywhere here that is independent of the resolution. It's just, it's invariant of the three manifold, invariant of X, independent of resolution. If you blow up, blow down, and also in higher dimension, you have to vary. It's not just a blow up a point. So what I want to say that here, this has a natural extension, the analytic lattice cohomology in higher dimension, but it's absolutely not clear that what's its pair, topological pair, no. Exactly the opposite side, no, it's missing. Yes? So from the ring, usually you can say nothing, because in higher dimension, the ring might have very trivial information. It sometimes can be even the sphere. Yeah. So it's not the. So here is the conjecture is that this fits in the topological side, the embedded compact homology of the ring. So that would be the pair in the higher dimension.
In the numerator also you have n, isn't it? The first term.
Here?
Yes, here, yes. It is hn. Oh,
Those are
n
just
minus
n minus 1.
Yes, and the numerator is 0, 8, 0.
O L.
No, on the
previous
term
term.
before this.
I don't know.
Yes, this dimension of.
Dimension over C. Dimension over C here. This is H0, H0. This is exactly the same as this one. So all the functions divided by the corresponding, you have a ideal filtration, divisorial filtration by ideas. Yes, and then that is the corresponding Hilbert function is here. Also here. So formally this is the same as this one. Yes. Then Hn minus 1 of 1. Oh, actually I should be careful, yes. So let's see the curve case. So again, of course, it's not so bad, that we go to the normalization. So if I have S irreducible components, then the normalization is how we say, and then we have also corresponding to the, say, divisorial filtration, we have so the evaluations, yes, for each connected irreducible component, we have the corresponding evaluation, and again we have the corresponding Hilbert function that we consider all the functions, and using the multivariable variation, we have the functions which have order higher than corresponding R. Then we have the Hilbert function, and here the weight function is defined 2 times h minus the sum of Li's. Actually, this looks a little bit different than this. Actually, using the Rosenlich differential forms, you see, so this tells us that somehow it's a pair between Hilbert and some top differential forms. And also this, also this can be written at h minus another object, but here it's very special in this case. So you have some duality or some, and I didn't want to introduce differential forms here, so I just defined, and this is the equivalent definition. And then again you have H cohomology theory, and turns out actually you have to work with it, yes, that the Euler characteristic is the delta invariant of the plane curve, of curve. So it's not just any curve, it's the delta invariant. Actually, it's maybe it's, I don't know if in this talk I can suggest or not, but sometimes it's not so easy to compute anything. So I have a resolution graph of this 10, or I don't know, again, 10, 20, or I don't know how many, it's a lattice. So it's really, you need some techniques. So to reduce the number of lattice, or the rank of the lattice, or to do some surgery formula. So it's here the computations are not easy. On the other hand, but here you have a chance because it's combinatorial. Maybe it's a little bit easier. But here in the case of analytic definitions, and even in the curve case, these Hilbert functions are not so easy because you need the analytic type, yes, and then the functions, and so the computations are not very easy. Maybe some properties. So in the case of curves, so we use the Hilbert function. Actually, the Hilbert function can be, it's an output of the semigroup. The semigroup it's well defined in any range, so not just when it's we have one irreducible component. It's a monoid basically in Z to the S, and so this semigroup actually it's already gives also H, and from H we have the weight function, so we have the lattice homology. And it turns out that we don't really need everything. So actually it's enough to consider one rectangle. And this is the conductor of the semigroup. And just we need that S-dimensional rectangle between 0 and the conductor. and in that we consider the weight functions on that rectangle, then we have that already contains all the information, because what is far can be contracted and has no additional information. And also when it's Gorenstein, when a curve is Gorenstein, then you have even a symmetry between the zero and the conductor. That is somehow it's corresponding to the Gorenstein symmetry of the curve, and also of the semi-group. In higher rank, it's very tricky, the formulation of the symmetry of the semi-group. But anyway, the wave function is symmetric with respect to 0C rectangle, and it's enough to consider that rectangle, so we will have a symmetry of the cohomology as well. And indeed, we have examples also when there is H1, H2 non-trivial. I don't know what time, so I have time to make a
15
picture.
minutes, yeah.
15 minutes. Actually, it's, yeah, maybe it's not enough to I wanted to make here a picture, but maybe at the end, if I will have time, I will show you an example of this, but can be a homework also, that x squared plus. Of course, that if I want H1, I need at least rank 2, yes? Oh, it's clear, yes? H2 to 5, and I consider the symmetric one. And in this case, maybe I put here the H0 or the graded root. The graded root is here, I have 1, 2, 3. That is at the -2 level. At the -1 level, everything is connected. That is the -1. At 0 level, I have of the 0 cycle, I have the generic, and here is the conductor, and starting from 1, it's connected. Actually, it's possible to prove that starting from 1, it's connected. But it's the proof, it's tricky. So it's we need some really topology or the properties of the semigroup. So this is H0 and H1. Actually, H1 is we have two Z2s and both in degree -1. So I have.
You are writing the homology of that singularity?
This singularity, that's right. This singularity, yes, if I have irreducible, then everything is on a rank 1, so I have just connected component. Yes, so maybe we have also some other examples, but here, if I will have time at the end, I can make a picture that how you see in the plane, what is the weights, and what are the essence, that here is some cycle appears. Very good.
So how is this related to the semi-group, or can you like?
Yes, the semi-group is actually, you see, so in this case the H is that how many functions you have. The semi-group is exactly the elements where those are exactly the variation of the functions. So when the semigroup is present, then that is the present of function. So in the Hilbert function, you have a jump 1. And actually, in the case of curves, you can show that that is exactly jump 1. So it's somehow the position of the semigroup tells you very nicely the. Of course, that is very interesting when you have higher ranks, that where are the semigroups, where are conductor. So, but you have the multiple of the Hilbert function. So actually, in all my computation, I'm using sometimes the semigroup. But you see, even the semigroup, I give you a singularity in the plane curve case. We have actually even there, it's not so easy to compute the Hilbert function. What I'm using, it's a formula proved by me and Gorsky in a joint article. But in higher, so it's not embedded dimension is arbitrary to find the semigroup or the Hilbert function. It's interesting. Well, let's see some other examples. So so this is actually the case of the three coordinate axes. Yes, three coordinate axes in C3. Yes, that is not Gorenstein, not a plane curve, but not even Gorenstein. So this is actually delta is 2. It's well known. This is that is exactly the bounds for the delta. If I have 3 components, then delta should be bigger than 2. R minus S minus 1. These are exactly the how to say, the sharp cases when the inequality is realized, and this is exactly then the H0, H1 here it's vanishing. Actually, you can take another with delta 3 non-Gorenstein. When I take, say, the semi-group, I take 0, it's there, 1, 2, it's out, gap, delta 2, and starting from 3, everything is in the semi-group. So the semi-group generated by 3, 4, 5, yes, take that one. Take the ring associated with CS, associated with the semi-group. Take the spec, that's again a curve singularity, yes, embedded dimension 3, and that also has this one. And the symmetry, it's exactly, this is symmetric, that is 0, that is C, that is, these are the plane curves are symmetric, this is not symmetric, actually it's compatible with the fact that it's not Gorenstein. So here I have the 3 lines in C2, these are the 3 axes in C3, this is the 3 line, that has delta 3, and this is the graded root, and yeah, and then here I wrote another one, actually this is exactly here, I forgot that, okay, so that is that. So I want to discuss a little bit about the deformations, of course, and actually this is the main. I really hope that will be a good application, because this structure is really strong. So in general, we have dimensions of spaces associated with deformation, or the invariance of dimension of spaces, and we have semi-continuity, but usually they are not sufficiently strong. Of course, that we know also that in the plane curve case we have the spectrum semi-continuity, which is very strong, but still it's not enough, and we're searching for other invariants which would measure that some deformation exists or not. But again, the spectrum of the Hodge given by mixed Hodge structure, that is the vanishing cohomology, that is for plane curve singularities or hypersurface singularities we have. So in general, we cannot use. Here I want some deformation, and embedded dimension it can be higher, can increase or decrease, or yeah. But let's take, for example, this singularity, and yeah. So here again, just some examples that here the number of components, it's really completely different. You see, that's what I want to suggest, that here the lattice where I compute, it's completely different. One is 1-dimensional, the other is 3-dimensional. You have the different, how to say, level sets, and then compute the cubes and everything. And it turns out, for example, this deformation is delta constant deformation, and the root is stable. And also I consider here this one, that is a plane curve is two Puiseux pairs, irreducible 2 Puiseux pairs. Here it's I perturb the first Puiseux somehow, the first term, and I will have 2 irreducible components, and Milnor number jumps. It's not equisingular. The embedded dimension completely, yes, even the number of components is different. Well, it turns out that it's delta A constant, it's a delta constant deformation, and the graded root somehow is constant. So it's at some point I even conjecture, or I saw that it's true that this is constant along the delta constant deformations, but it turns.
Could you remind me what S was?
S is the number of irreducible components. What is the rank of the lattice? Yes. So how many variations we? Yes. So the rank, this lives in Z. Say that this is in Z3 when we make the lattice. Yeah. And also here, yes, irreducible, and this splits in 2. So actually, it's not true that delta constant deformations. I saw that, okay, this is a beautiful method to test or to see that delta constant deformation. That is an interesting question in the formation of singularities. Where it turns out that is not true, actually, but this some of the deformations, delta constant deformation, are really interesting, special, and this is one of the special. I don't want to explain what is the meaning of exactly this special, but here it's an example when you see this is irreducible, here is the semi-groups of this, so the number of gaps is 3. So here, just using the Hilbert function, how many elements I have left from that. Here, if I cut, it's 1, 1, 1, is left from this 2, 3, so that is actually the Hilbert function, and after that we symmetrize because that is Gorenstein, and here is the for the deformed I have 2 components, and and it turns out that this jumps, and then you can even see that what is happening at the deformation level, that these 2 elements here, actually there are these 2 zeros, and here actually these 2 zeros, actually here is a +1 between them, here is a -1 between them, it's already the difference. So it's very tricky, just one number somehow goes in a different way, and all the lattice cohomology it's different, but somehow these measures, that very, I don't know, accidental way that there is a 0 or 1 or -1, you can say, it doesn't matter. Well, it matters. So it's not a delta constant. So let's see a little bit more about deformations. So that is a harder part, actually, that if I have a deformation of reduced singularities, then we really have a ZU module morphism. So actually what we have is at the level of SN spaces. We compute, again, I want to emphasize, in the next page we'll be asked for that the lattices are completely different. So the number of irreducible components can go up, down, so it's the lattice where you consider the weight functions are very different. Yes? But on the other hand, one can prove that the SN spaces for t not equal 0, yes, it's included in the SN space, or at the n level of the central one. So maybe also here we see that this is the t not equal 0, so here this is the 2, it's included in this one. Sometimes it's different, sometimes jumps, but you have an inclusion. And this at the graded root level gives a morphism, say, from t not equal 0 to t0, and then cohomological level gives this morphism. And that is preserves all the SNs, so it's a graded, and also the inclusions, the tower is preserved, so it's a ZU module structure, so we have a graded ZU morphism between the graded cohomologies. And also if you want the roots, then intuitively it's in opposite direction goes, because it's homological, say that how we contract the connected components of its homological operator, we have a morphism.
So can you say something about like surjective, injective?
In general, it's not surjective. In general, it's not injective. So that is exactly, you see here is the example. Even if delta constant, even if the Euler characteristic is preserved, then you see what is happening, that when this is the deformation, that this goes here, these 2 points joint in this one, and you don't hit this one. So it's not injective, not surjective. Surprise. Yeah, but of course that's on the other hand, we have a long exact sequence because we have the inclusion of SN spaces. So we have, of course that's the next step. I will not explain this, that what is exactly this, the interpretation of the non-injectivity, non-surjectivity of this map. So again here I just, so let's see, I give you one example when we really see somehow it's hiddenly, it's in the literature what we need to prove that this functor exists. And I will assume for this that the central one is irreducible. If the central one is irreducible, then of course that in that case that is just a z. And there is a very natural, of course, the map, just L goes to the sum of L I. So that L is L1, L2, Ls, and we consider to make the summation. Somehow it's natural map, And it turns out that is in some other reasons we proved with Julian Revalski that we have somehow semi-continuity of the Hilbert functions. So this Hilbert function has these inequalities through using the deformation. So here is this exactly this lattice map, and then they can be compared. And this is enough now, using the weight function definition, that this, we have a map. Extends to map, the essence levels, so that really gives here, gives the, yes, if I have the inclusion at the level of maps, then I have automatically the homological, because the homology of SNs defines the lattice homology, so it's enough to realize the level sets are somehow. So this is the key. This is the key. And in this case, it was possible somehow using this inequality, semi-continuity of the. Actually, this is some kind of semi-continuity of the Hilbert form, semi-continuity of the semi. Yes. But again, I want to emphasize that here the ranks might jump. Well, this is hard to judge. Actually, even at that time we tried because of different other reasons and then other. What is the generalization of this? It's not so clear. And it's not so, in general, you don't have a nice map at the level of lattices, which extends this property. So it's this, to prove that something like this exists, then one needs completely different arguments. So yes, it's different. Again, this is already added that also the number of components in beta dimension can vary. Also the delta around this deformation, but really what is the hope that using this technique or this tool now we can attack the problem of, you see that is an open problem that what singularity can be deformed in what, and this is sufficiently rich, yes, it's not just a number, you have a ZU module structure and probably this tells you more and then you can read the abstractions better and then maybe I don't know if even if not an if and only if statement, but something that's a good tool. Again, I want to emphasize that if I have a plane curve, then all these Hilbert, semi-book Hilbert function embedded topological type, they are complete topological invariants, and they provide this one. But in this case, we have actually we extend, yes, for any embedded dimension higher than 2 using the semi-book Hilbert function. So it's, for example, in the case of Hegar-Fleur knot or link Hegar-Fleur, it's not so clear that, okay, how to extend that is really special for embedded topological type, yes? And then, but here, using this rigidity or analytic definition, we can extend. I think that this is what I wanted, so that is my last page, and I think that it's also the time. Thank you very much.
Any questions?
I have a question about the Milnor number.
Yeah.
So you consider delta constant families and the H star changes, and well, it has to be due to the change of the Milnor number.
Yeah.
So how do you capture the Milnor number?
Yeah, so but
with
yes,
H star?
Milnor, yes, of course that. Yeah. Well, I'm working also on the Milnor number. So what is the category? This is the category of delta invariant, and of course one of my steps, so it's we work on the categorization of the Milnor number also. It's not so. There are some natural extension, but you see that's really when you have say a convergence theory, you need some tests. That's really the good choice of the definitions so I don't know what was exactly the question.
I mean,
yeah, you get a Milnor number, but even if the Milnor number I fix, yes, or if the Milnor number is fixed, then the deformation is trivial. Yes.
No, what I wanted to say is that the Euler characteristic of H star is the delta invariant. So how do you compute the Milnor number from H star?
Yeah, for me, you need to compute. Yes, it's not so evident. Actually, you cannot. Because you don't see the even you see I had some examples when delta constant but different number of irreducible components, and therefore constant was the H star was the same. So the same as H star, and the minimum numbers are different. So if we want the minimum to concentrate on minimum number, you need a different, that you need a categorification of the minimum. On the other hand, this also tells you something, because the data is pretty close. You see, we know the Buchwald's formula, yes, Buchwald's Graya formula. So in the
any more question? If my understanding is correct, so in the case of curves, you have this some calculation of Acad homology, embedded homology, and this is some kind of generalizing this calculation scheme. And something which tells for me is that if you go higher dimensions, then it is known that nothing similar to Acad homology or embedded contact homology exists. But you mentioned that there are something higher dimensional analog of this. So,
yes, so
are there any reason that you can expect?
So the analytics, so this lattice homology, yes, you can define, yes, so in any dimension. So that is actually amazing. So for any dimension isolated singularity, you have some similar picture than the ZU graded as a Hegar-Fleur or a monopole homology or this.
So in this sense, that one is invariant?
It's invariant of the singularity. It's independent of the resolution, that is proved. Independent of the resolution, it's invariant
but
of the
it's not
singularity.
topologically invariant, probably.
It's not topological. It's
I see.
and yeah, and did I mention in this case it's very interesting that say I fix a topological type and I have a cohomology or graded or something, and I consider different analytic structures on the same link, and these jumps. The analytic lattice jumps. It's depending how special or what is missing, what function cannot be realized, you cut some legs from the topological one. So it's this also measures how is the variation of the analytic structure.
So maybe higher dimensional Hegel homology does not exist, but maybe embedded contact homology might be. So if it exists, it might be a calculation?
Yeah, that is probably, even I wrote here, the embedded contact, I was told that this is not really defined totally, it's not in higher dimension.
No, higher dimension is not defined.
No.
Contact homology, yes, but embedded is...
Yeah, so, but I don't know what version here we should, but I think that embedded, because the embedded contact homology in dimension, in the surface case, it fits with the Hegar-Fleur, so it's, here really it's needed embedded. I started to read it, but I was told that there's some, yeah, you know much better. But that is speculation. That should be the pair if we want to go back to the topology.
But a priori, it's not clear that there is a pair at all.
Yeah. So in what sense is pair? That if the analytic structure is nice in some case, then probably fits. Is the topological, is weighted homogeneous or something, then has a chance. If you destroy, you take a very generic analytic something, then completely different. Then there is no, in that sense, or somehow that bounds.
Have you thought about quasi-ordinary singularities as a natural generalization of the curve singularities?
No, that's a project. I have some family. Yeah, so we computed some families, but in higher dimensions.
Yeah.
Well, it's interesting.
Any further questions? So maybe this is the last talk, and we thank the organizers, all the organizers, for this very nice conference.
Thank you very much for coming, and so hope we have another great conference for the year. Thank you.